Crocodile paradox. Imagine standing at the riverbank, heart pounding, as a crocodile stares back at you with cold reptilian eyes. Your child has just been taken by this creature, but instead of devouring them, the crocodile makes a strange offer. "I will return your child," it says, "if and only if you correctly predict what I will do next." You're frozen, not just by fear, but by the impossible logic you now face. This is no ordinary threat. It is a trap woven with paradox. What you say next could determine everything, and yet, no answer seems safe. This is the crocodile paradox, an ancient thought experiment that reveals the bewildering consequences of self-referential statements. At first glance, it might seem like a mere riddle, but buried inside is a profound exploration of logic, language, and contradiction. Consider your two possible answers. If you predict that the crocodile will return your child, and it does, your prediction was correct, and the agreement is satisfied. But if it doesn't, your prediction was wrong, and the crocodile has no obligation to return the child. So far, so consistent. But what if you predict the opposite, that the crocodile will not return the child? If it was planning to keep your child, your prediction is correct, which means it now must return the child. But that contradicts its plan, and if it was planning to return the child, your prediction is incorrect, and by the terms of the deal, it shouldn't return the child after all. The crocodile is trapped. No matter what it does, it violates the condition it just imposed. This paradox reveals something essential about logic. When rules turn in on themselves, they often collapse. It's a haunting reminder that not all dilemmas can be solved, and sometimes questions are designed not to be answered, but to show us the limits of our understanding. Liar paradox. Imagine someone looks you straight in the eye and calmly says, "I am lying." Just 4 simple words, and yet they unleash a storm of contradiction that has baffled thinkers for over 2,000 years. If the person is telling the truth, then they are lying, which makes the statement false. But if they are lying, then they are not lying, which makes the statement true. The mind folds in on itself, caught in an infinite loop with no resolution. This is the liar paradox, one of the oldest and most enigmatic logical puzzles in human history. It sounds harmless, even amusing, but beneath its surface lies a profound disruption to how we understand truth, language, and reality itself. The origins of the paradox trace back to ancient Greece, with the philosopher Epimenides, who reportedly said, "All Cretans are liars," despite being a Cretan himself. This evolved into the more modern form we know today. This statement is false. It's a sentence that refers to itself, and in doing so becomes logically unstable. If it's true, then it's false. And if it's false, then it must be true. It traps the listener in a loop that logic cannot untangle. The liar paradox isn't just a linguistic curiosity. It exposes the limitations of formal systems and the fragile boundary between meaning and contradiction. Philosophers and mathematicians have tried for centuries to resolve it. Some argue that such sentences are simply meaningless. Others propose new systems of logic that allow for statements to be both true and false, a concept known as dialetheism. Still others suggest we need a hierarchy of language, where statements about truth cannot refer to themselves. But none of these approaches has completely dispelled the paradox. It lingers, quietly undermining our confidence in the stability of language, and maybe that's the real power of the liar paradox. It doesn't just confuse us. It humbles us, reminding us that even the simplest sentence can open the door to infinite uncertainty. Barber paradox. In a quiet village, there lives a barber with a peculiar rule. He shaves all and only those men in town who do not shave themselves. At first, it sounds like an efficient arrangement, a tidy little system that keeps everything in order. But then someone asks a simple question: who shaves the barber? And with that, the entire structure collapses. If the barber shaves himself, then he must not shave himself, because he only shaves those who do not. But if he doesn't shave himself, then he must shave himself, because he shaves all those who do not. The logic twists in on itself, creating a contradiction that cannot be resolved. This is the Barber paradox, a thought experiment introduced by British mathematician and philosopher Bertrand Russell to illustrate the deep and often hidden inconsistencies that can exist within set-based logic. At first glance, the paradox might seem trivial or amusing, but like many paradoxes, its simplicity is deceptive. It reveals a profound problem about how we define sets and membership, specifically the problem of self-recognition. In the barber's case, the set is defined by who the barber shaves, and yet the barber himself becomes part of the very set he's meant to define. The definition loops back onto itself in a way that makes it logically impossible to complete. This isn't just a linguistic trick, it's a foundational issue in formal logic and mathematics. Russell used this paradox to highlight a similar issue in set theory, which was being developed at the time to form the basis of all mathematics. If we allow sets to contain themselves, we risk encountering contradictions just like the barber's dilemma. His insight led to major revisions in how mathematicians thought about logic, ultimately giving rise to new systems that try to avoid such paradoxes. But the core of the Barber paradox remains unresolved, a simple question with no simple answer. It's a reminder that even the most ordinary scenarios can unravel into profound confusion when logic meets self-referential. Paradox of the unexpected hanging. A prisoner is told by a judge that he will be hanged at noon on one weekday in the coming week, but the exact day of the execution will be a surprise. He will not know the day of the hanging until the executioner arrives at his cell door. At first, the prisoner is terrified, but then he begins to think. If the hanging were to take place on Friday, he reasons, then by Thursday night he would know there was no other day left, so it wouldn't be a surprise. That rules out Friday. But now if Friday is out, then Thursday must also be out, because if he's not hanged by Wednesday night, Thursday becomes the only possible day left, and he would expect it. The logic continues. By this reasoning, he eliminates Wednesday, then Tuesday, and finally Monday. He concludes that a surprise hanging is impossible. But when the executioner arrives on Wednesday, the prisoner is completely shocked. The judge's promise is fulfilled. The hanging is unexpected after all. This is the paradox of the unexpected hanging, a haunting and deeply puzzling scenario that challenges our understanding of logic, prediction, and knowledge. The paradox hinges on the prisoner's attempt to logically eliminate all possible days, assuming that a true surprise must be logically impossible to anticipate. But the very act of that elimination blinds him to the real possibility that the execution might still come as a surprise. His reasoning seems airtight, and yet it fails in practice. How can something be logically impossible and yet still happen? Philosophers have debated the implications of this paradox for decades. Some see it as a flaw in how we define surprise. Others view it as a clash between logical deduction and real-world uncertainty. It reveals how the mind can trap itself in perfect reasoning that leads to an imperfect understanding. And in doing so, it reminds us that not all truths can be known in advance, no matter how carefully we think them through. Two-envelope problem. You're presented with two sealed envelopes. Inside each is a sum of money, and you're told that one envelope contains exactly twice as much as the other. You pick one at random, say envelope A, and before opening it, you're offered the chance to switch to envelope B. You begin to reason, suppose envelope A contains $100, 0 cents. Then envelope B could either contain $50, 0 cents. If that's true, then there's a 50% chance of gaining $100, 0 cents, and a 50% chance of losing $50, 0 cents. That sounds like a good gamble, because the expected value of switching is higher, so you switch. But then the same logic applies again. You start thinking you should switch back. No matter which envelope you hold, it seems like switching always gives you a better deal. And yet that can't be right. You can't keep gaining value by switching envelopes forever. Somewhere your reasoning must be flawed. This is the two envelopes problem, a deceptively simple paradox that has fascinated mathematicians, philosophers, and economists for decades. The crux of the paradox lies in expected value, a concept used to weigh outcomes in uncertain situations. The calculation seems to suggest that switching always gives you a higher expected value. But here's the catch. Once you assign a specific dollar amount to the envelope you've chosen, your reasoning becomes tangled in circular logic. If you assume the other envelope contains either half or double that amount with equal probability, you're making assumptions that don't hold up statistically. The probabilities aren't symmetric and the values you're comparing aren't independent of one another. The paradox reveals a subtle error in how we think about probability and expectation. It shows that applying mathematical reasoning to uncertain outcomes can sometimes lead to absurd conclusions when the underlying assumptions are flawed. In reality, without any extra information, both envelopes are equally likely to be the better choice. The two-envelope problem reminds us that not all choices can be improved by overthinking, and sometimes the best decision is simply to choose and stop switching. Lottery paradox. Imagine a lottery with 1 million tickets and only one winner. You know the odds, you're holding a single ticket, and you logically conclude this ticket will probably lose. In fact, you could say that about any ticket in the pile. Each one has only a 1 in a million chance of winning. For every individual ticket, it seems entirely reasonable to believe it will lose. But here's the twist. One of them must win. So how can it be rational to believe of every single ticket that it will lose, while also believing that one will win? This is the lottery paradox, a troubling problem that reveals the gap between what's probable and what's certain, between individual beliefs and collective reality. At its heart, the paradox challenges how we deal with rational belief in the face of overwhelming probability. It's rational to believe that ticket 1 will lose, and ticket 2, and ticket 3. You could go down the entire list and confidently say that each one is a loser. But taken together, these perfectly reasonable beliefs lead to a contradiction. If all the tickets lose, then no one wins, which directly conflicts with your belief that the lottery will have a winner. You end up holding a set of beliefs that are individually reasonable, but collectively inconsistent. This paradox doesn't just apply to lotteries. It shows up in everyday reasoning whenever we try to apply logic across multiple uncertain outcomes. It raises difficult questions about the nature of rational belief, especially when dealing with large sets of uncertain events. Should we revise our standards for belief to avoid contradiction, even if it means believing less strongly in each case? Or should we accept that sometimes rational belief can be internally inconsistent? The lottery paradox forces us to confront the fragility of reason itself and reminds us that even our most logical judgments can falter when stretched across 1,000 possibilities, each just shy of certainty. Sorite paradox. How many grains of sand make a heap? 1 grain clearly isn't a heap. 2 grains don't make a heap either. Add a third and it still doesn't seem like enough. So when exactly does a collection of grains become a heap? 10? 100? 1,000? The moment you try to answer this question precisely, the ground begins to shift beneath you. This is the Sorite's paradox, also known as the paradox of the heap, and it challenges our understanding of vague concepts, gradual change, and where we draw the line between one thing and another. It begins with a simple observation that tiny changes don't seem to make a difference. Removing 1 grain of sand from a heap still leaves you with a heap. Do it again and again and again. If each removal leaves you with a heap, then even 1 grain must still be considered a heap. But that's absurd. At some point it stops being a heap, and yet, you can't seem to find that exact moment. The Sorite's paradox isn't just about sand. It applies to all sorts of everyday concepts: baldness, tallness, wealth, age, even morality. When does a person go from young to old, from honest to dishonest, from poor to rich? These are gradual transitions, and yet we use words that imply sharp boundaries. The paradox shows that many of the categories we rely on are fuzzier than we like to admit. Philosophers and logicians have proposed various solutions. Some suggest that language is inherently vague and that we simply need to accept the ambiguity. Others attempt to introduce degrees of truth or fuzzy logic, where something can be sort of true rather than absolutely true or false. But no consensus has emerged. The Sorites paradox reminds us that life doesn't always fit into neat boxes. It teaches us to be cautious about certainty and to recognize that the world is often painted in shades of gray, not black and white. And in that subtlety, there's a quiet, enduring truth. Achilles and the tortoise. Achilles, the swiftest of all Greek warriors, challenges a slow-moving tortoise to a race. Out of fairness, or perhaps overconfidence, Achilles gives the tortoise a head start. The race begins, and Achilles charges forward with incredible speed. But Zeno, the ancient Greek philosopher, poses a question that unravels the logic of motion itself. Before Achilles can reach the tortoise, he must first reach the point where the tortoise began. But by the time Achilles gets there, the tortoise has moved a little farther. Now Achilles must reach that new point, but again the tortoise has moved ahead. No matter how fast Achilles runs, there are always more points he must reach, each one a little closer to the tortoise. Zeno argues that Achilles will never overtake the tortoise, because he must complete an infinite number of steps to do so. This is the paradox of Achilles and the tortoise, a thought experiment that shakes the very foundation of motion and infinity. At first, the paradox seems absurd. We know from experience that Achilles would easily outrun the tortoise. But Zeno's argument isn't about speed, it's about division. He breaks motion into infinitely many parts, and suggests that because these parts are infinite in number, the motion can never be completed. It's a collision between logic and reality, where common sense says one thing and pure reasoning says another. How can motion occur at all if it must pass through an infinite number of steps? The resolution to the paradox came centuries later with the development of calculus. Mathematicians showed that an infinite number of steps can sum to a finite distance, allowing Achilles to overtake the tortoise after all. Yet the paradox remains deeply symbolic. It reminds us that even the most obvious truths can be questioned. It invites us to explore the hidden complexities of space, time, and motion, and to see that sometimes the path to understanding lies in the pursuit of the impossible. Arrow paradox. Imagine an arrow soaring through the air. At every single instant in time, it occupies a precise location in space. For that brief moment, it is completely still, frozen in place, motionless. If time is made up of these individual instants, and at every instant the arrow is at rest, then how does it ever move? This is Zeno's arrow paradox, a puzzle that challenges our basic understanding of time, motion, and continuity. It begins with a simple assumption. If we divide time into indivisible snapshots, tiny, motionless moments, then motion becomes an illusion. The arrow is never moving in any single instant, so how can it move at all when all of time is just a collection of such instants? Zeno's paradox strikes at the heart of how we experience motion. We think of movement as continuous, fluid, and uninterrupted, but if we dissect it into parts, each one completely still, then motion vanishes under scrutiny. The arrow in every frozen frame is simply there, unmoving, and yet we see it fly. The paradox doesn't deny that we perceive movement. It questions how movement is even possible when built from moments that contain no motion at all. It's like watching a movie, one frame at a time. Each frame is static, yet when viewed together, they create the illusion of movement. But unlike a film reel, reality isn't just an illusion. Or is it? The resolution once again comes from mathematics, specifically the concept of limits and calculus. By treating time not as a collection of discrete moments, but as a continuous flow, we reconcile the paradox. Motion is not the result of what happens in each instant, but of how those instants change over time. Still, the arrow paradox remains more than a math problem. It's a philosophical mirror, reflecting the strange gap between perception and logic. It whispers a reminder that even the simplest truths, like an arrow in flight, can contain mysteries deeper than we realize. Ship of Theseus. Imagine a ship, sturdy and seaworthy, setting sail on countless voyages across the years. As time passes, its planks begin to rot, its sails wear thin, and its mast weakens. So, the crew begins replacing its parts, one board here, one rope there, until eventually every single piece has been swapped out. The ship still sails the seas and bears the same name, but is it still the same ship? This is the Ship of Theseus, Paradox, a timeless puzzle that questions the very nature of identity. At what point does something stop being what it was? Is it when the first part is replaced, the last? Or does identity somehow persist through change, even when nothing original remains? Now imagine this. Someone gathers all the discarded, weathered parts and rebuilds the original ship from them. Now there are two ships, the restored one made of original parts and the maintained one made of replacements. Which is truly the Ship of Theseus? Is it the ship that has continued to sail, growing through change, or is it the one rebuilt from the very materials that first gave it form? Both seem valid, yet they can't both be the original, can they? The paradox doesn't offer easy answers. It invites us to explore how we define continuity and sameness. This question stretches far beyond ships. Our bodies replace most of their cells over time. Does that make us different people than we were a decade ago? What about personal growth, memories, and experiences? Are we the same person through the years, or just the latest version of ourselves? The Ship of Theseus reveals that identity is not fixed in form, but fluid in essence. It challenges us to see identity not as a static object, but as a living process, an unfolding story. And perhaps that's the point. What makes something or someone real isn't the parts they're made of, but the journey they've taken and the meaning they carry through time. Russell's Paradox. Imagine a library that catalogs every book in the world, neatly organizing them into shelves and categories. Now imagine that one of those books contains a list of all books that do not list themselves. The moment you think about this special book, the logic begins to twist. If the book includes itself on the list, then by definition, it should not include itself. But if it does not include itself, then it should be on the list, and therefore it must include itself. This strange loop is a simplified version of Russell's paradox, a foundational problem in logic and set theory. Introduced by philosopher and mathematician Bertrand Russell in the early 20th century, the paradox reveals a contradiction at the heart of seemingly straightforward logic. To understand it in its original form, consider a set that contains all sets that do not contain themselves. Most sets are ordinary, a set of numbers, a set of books, a set of people. Some of those sets don't include themselves, like the set of all cats, which obviously isn't a cat. But what about the set of all sets that do not include themselves? Should that set include itself? If it does, then it shouldn't. If it doesn't, then it should. The definition collapses under its own weight. Russell's paradox exposed a major flaw in the foundation of mathematics at the time, particularly in set theory as developed by Frege and others. The contradiction shook the logical structure of mathematics and forced a reevaluation of how sets and definitions are constructed. It led to the development of more careful systems of logic, including type theory and axiomatic set theory, which sought to avoid these kinds of self-referential traps. Beyond mathematics, the paradox reveals the dangers of circular definitions and the complexity of language itself. It shows how even the most precise systems can unravel when self-representation enters the picture, and it reminds us that at the edge of every logical system lies a mirror, reflecting back the strange possibility that some questions undo themselves simply by being asked. Relling-Nelson Paradox. Imagine a language game where we divide all adjectives into two categories. Some adjectives describe themselves. These are called autological. For example, short is a short word, so it describes itself. English is an English word. Polysyllabic is polysyllabic. These adjectives match the very quality they express. Others, however, do not describe themselves. These are called heterological. For instance, long is not a long word, and French is not a French word. Silent is not silent. It sounds like a clever and harmless distinction until you reach one particular word. Heterological. Is the word heterological itself heterological? This is the Grelling-Nelson paradox, a linguistic puzzle that collapses under the weight of its own classification. Let's try to solve it. If heterological is heterological, that means it does not describe itself, but that would make it autological because it fits the definition of being heterological. On the other hand, if heterological is not heterological, if it does describe itself, then it fails its own definition. Because heterological adjectives are supposed to describe words that do not describe themselves. The result is a contradiction, an infinite loop where the definition of the word negates itself. Much like the liar paradox, where someone says, "This statement is false," the Grelling-Nelson paradox breaks the rules of logic using the logic itself. This paradox isn't just a trick of language. It's a mirror showing the limits of self-referencing. It reveals how definitions, when turned back onto themselves, can become unstable. Philosophers and logicians have long studied such paradoxes to understand the boundaries of meaning, reference, and language. In trying to define what is heterological, we end up with a sentence that undermines its own foundation. The Grelling-Nelson paradox reminds us that even in the structure of language, there are traps, deep paradoxes that unravel clarity. It's a quiet whisper that says not every word can be neatly labeled, and not every question has a place within the framework it tries to question. Omnipotence paradox. Can an all-powerful being create a rock so heavy that even they cannot lift it? At first, the question sounds like a clever riddle, a trick of words, but behind it lies a deep and ancient dilemma known as the omnipotence paradox. It strikes at the core of what it means to be truly all-powerful. If the being can create such a rock, then there's something they cannot do, lift it. But if they cannot create the rock, then there's something else they cannot do, create it. Either way, there seems to be a limit, and the idea of unlimited power begins to unravel. How can absolute power contain a contradiction? This paradox has haunted theologians and philosophers for centuries. It challenges the coherence of omnipotence by forcing it into a logical loop. If power includes the ability to perform the impossible or contradictory, does it still make sense to call it power? And if there are things an all-powerful being cannot do, like make square circles or four-sided triangles, are those really limits, or just a misunderstanding of what power means? One way to resolve the paradox is to argue that true omnipotence does not include the ability to do the logically impossible. Creating a rock so heavy that it cannot be lifted by the one who created it is not just a difficult task, it's a contradiction in terms, like drawing a number that is both even and odd. In this view, logical contradictions are not things at all, but meaningless combinations of words. Others take a different approach, suggesting that omnipotence must be redefined or reinterpreted. Some propose that an all-powerful being can do anything that aligns with their nature, but not acts that destroy their own identity. The omnipotence paradox reminds us that even the grandest ideas, like infinite power, are still bound by the subtle, unyielding laws of logic. And perhaps that's the true mystery, not in what power can do, but in what it must leave undone to remain coherent. Paradox of the ravens. Imagine you want to test the statement, "All ravens are black." One obvious way to verify it is to look at ravens. If you find a black raven, the statement holds up. If you find a red or white one, it fails. But here's where things get strange. The statement, "All ravens are black," is logically equivalent to "everything that is not black is not a raven." So, if you look at a green apple and confirm that it is not a raven, you've technically gathered evidence supporting the original claim. This is the paradox of the ravens, also known as Hempel's paradox, and it reveals a deep problem in how we understand confirmation and evidence. On the surface, this logic seems ridiculous. How can observing a green apple possibly tell us anything about the color of ravens? Yet by the rules of formal logic, it does. Every non-back, non-raven you observe eliminates one more potential counterexample to the statement, all ravens are black. The paradox emerges from the gap between logical equivalence and intuitive relevance. It shows that the rules of confirmation theory, how we gather and validate evidence, don't always align with our instincts about what should count as meaningful data. Philosophers have tried to resolve this paradox in different ways. Some argue that while the logic is valid, the green apple offers extremely weak evidence, so small that it's practically irrelevant. Others suggest refining our understanding of confirmation to include context and background knowledge, allowing us to separate useful observations from trivial ones. The paradox serves as a reminder that logic alone doesn't always capture the full story of how we understand the world. The paradox of the ravens challenges our faith in evidence, in categories, and in the very process of learning through observation. It quietly suggests that even when logic is airtight, meaning may still slip through the cracks, leaving us to question not just what we know, but how we know it. Moore's paradox. Imagine someone looks out the window on a rainy afternoon and calmly states, "It's raining, but I don't believe that it's raining." The words are perfectly grammatical, each part makes sense on its own, and yet taken together, something feels deeply wrong. How can someone truthfully say that it's raining while also claiming not to believe it's raining? This strange dissonance is the heart of Moore's paradox, a philosophical puzzle named after British philosopher G.E. Moore, who first identified it in the early 20th century. It's not a contradiction in logic, but it is a contradiction in thought, in perspective, in what it means to believe what we say. The paradox arises from the strange tension between first-person knowledge and belief. It seems absurd for someone to say something they do not believe, especially when that something is a statement about their own perception. If you say, "It's raining," the assumption is that you believe it. But if you immediately add, "I don't believe that it's raining," you're undercutting your own assertion, not by fact, but by attitude. The paradox doesn't lie in the statement being false. It lies in it being unassertable. No rational speaker, in normal circumstances, could genuinely utter that sentence and mean both parts sincerely. Moore's paradox reveals the delicate structure of belief and language. It shows that belief isn't just about holding facts in our minds. It's also about consistency between what we claim and what we accept as true. The paradox challenges the idea that belief and truth can be treated separately, especially in our own minds. It forces us to consider the strange space between saying something and truly meaning it. In a world where people often speak for appearance, for persuasion, or for pretense, Moore's paradox stands as a quiet whisper of introspective clarity, reminding us that truth is not just about what is spoken, but about the invisible alignment between belief and voice. Paradox of analysis. Imagine trying to define a concept so clearly, so precisely, that there is no room for confusion. That's the goal of analysis, to take a complex idea and break it down into simpler parts. But what happens when the definition you offer is either too obvious to be useful or too different to be correct? This is the paradox of analysis, introduced by G.E. Moore, and it strikes at the heart of philosophical clarity. If your analysis is accurate, it should preserve the meaning of the original concept. But if it truly preserves that meaning, then it seems tautological, just repeating what we already knew. On the other hand, if it tells us something new, then perhaps it's not a faithful analysis at all. Take, for example, the statement, "A brother is a male sibling." If someone already understands the word brother, this analysis offers nothing new, it's just a restatement. But if someone doesn't already understand brother, how would male sibling help? The dilemma lies in this. For an analysis to be informative, it must differ from what we already believe, yet for it to be correct, it must capture exactly what we already mean. How can it do both? Moore's paradox forces us to consider the fragile space between explanation and identity. It shows that the process of defining concepts may be inherently limited. Philosophical analysis, rather than delivering simple clarity, often loops back on itself, caught between redundancy and error. The paradox is not about contradictions in logic, but about contradictions in purpose, between being enlightening and being equivalent. The paradox of analysis reminds us that the search for clarity can lead us into deeper fog. It challenges us to accept that some ideas resist dissection, not because they are unclear, but because they are already as clear as language allows. And in that, perhaps, lies a different kind of truth, one that can be understood, but never fully unpacked. Preface: Paradox. Imagine an author who has written a detailed, carefully researched book. At the beginning, in the preface, they include a humble note. While I believe every statement in this book to be true, I also acknowledge that there may be errors. On the surface, this sounds perfectly reasonable, but look closely and a contradiction begins to emerge. How can the author believe that every sentence is true, while simultaneously believing that at least one might be false? This is the preface paradox, a subtle and fascinating problem in epistemology, the study of knowledge and belief. It reveals the tension between individual confidence and collective doubt, between what we believe piece by piece and what we accept as a whole. The paradox arises from a clash between two kinds of rationality. On one hand, it's rational for the author to believe each statement in their book, since each was researched, considered, and written with care. On the other hand, it's also rational to acknowledge that, given human fallibility, at least one of those statements is probably incorrect. Typos, misinterpretations, or overlooked data make perfect accuracy unlikely, so the author finds themselves in a paradoxical state, believing every sentence, while also believing that not all sentences are true. This isn't just a problem for authors. It mirrors a common situation in daily life. We often hold multiple beliefs, each one individually justified, while also believing that some of our beliefs, somewhere, must be wrong. The preface paradox forces us to confront the limits of certainty. It shows that belief is not always additive, that a collection of perfectly rational beliefs can, together, lead to irrational conclusions. Ultimately, the preface paradox doesn't tell us to abandon belief, but to hold it with humility. It invites us to accept that rational thought includes room for error, and that wisdom often lies in the quiet space between confidence and doubt. Bootstrapping paradox. Imagine a scientist in the year 2300 receives a mysterious manual on how to build a time machine. She follows its instructions precisely, and after years of work, she constructs a functioning time device. Wanting to ensure this knowledge survives, she travels back in time and gives the manual to a younger version of herself, or perhaps to someone in the past who will later pass it on to her. Here's where the logic begins to twist. Where did the manual originally come from? It wasn't invented. It wasn't discovered. It simply exists in a closed loop, with no clear point of origin. This is the bootstrapping paradox, also known as the ontological paradox, and it challenges everything we think we know about causality, information, and creation. The paradox gets its name from the phrase, pulling oneself up by one's bootstraps, an impossible act that mirrors the circular logic involved. Something exists, not because it was created or evolved, but because it was passed from one point in time to another, by itself. A person receives knowledge, an object, or even an idea, and then becomes the source of it. Looping through time without an origin, the problem isn't just about time travel, it's about where things begin. Can something exist without ever being invented? Can knowledge appear without anyone having discovered it? The bootstrapping paradox shows how time travel, even in theory, disrupts the basic structure of cause and effect. It opens the door to self-creating objects, people, or information that defy logical beginnings. In storytelling, it creates fascinating loops, characters who become their own ancestors, or messages that have no author. But in philosophy and physics, it raises uncomfortable questions about identity, reality, and the limits of explanation. This paradox reminds us that time, as we understand it, may not be as linear or simple as it seems. And in that looping uncertainty, we find a quiet, unsettling truth. Not everything must begin somewhere. Some things may simply be, forever cycling through the strange logic of time. Paradox of tolerance. Imagine a society that prides itself on tolerance, a place where every voice is heard, every belief respected, and every person free to express their views. At first, this seems like the ideal foundation for peace and coexistence. But what happens when an intolerant ideology enters this tolerant society? One that seeks not dialogue but domination. If the society tolerates the intolerant in the name of freedom, it risks being destroyed by those who reject tolerance altogether. Yet, if it refuses to tolerate them, it becomes, in a sense, intolerant itself. This is the paradox of tolerance, introduced by philosopher Karl Popper, and it exposes a vital tension at the heart of every free society. The paradox asks, should a tolerant society tolerate intolerance? If it does, it may enable the rise of those who would eventually eliminate tolerance itself, closing down freedom of thought, of speech, and of difference. But if it does not tolerate the intolerant, then it appears to contradict its own values, acting against the very principle of open acceptance it claims to uphold. This is not just a theoretical dilemma, it's a real-world problem that has shaped the history of democracies, revolutions, and cultural struggles across centuries. Popper's solution is sharp but necessary. A tolerant society must be prepared to defend itself by being intolerant of intolerance, not to silence disagreement or criticism, but to protect the conditions that make tolerance possible in the first place. The paradox reminds us that tolerance is not the same as passivity. It is an active, ongoing choice to create space for others, one that requires boundaries to survive. In a world where extremism often hides behind the language of free speech, the paradox of tolerance warns us, if we are not careful, our openness can be weaponized against us. And so, to preserve tolerance, we must sometimes draw the line where tolerance ends. Paradox of the court. A young man named Euathlus wished to become a lawyer but lacked the money to pay for his education. He approached a well-known teacher, Protagoras, who agreed to train him under a unique condition. Euathlus would only pay for his lessons once he won his first case in court. The arrangement seemed fair. Protagoras would be compensated only when his student proved his success. Frustrated, Protagoras eventually sued him for the payment. And this is where the paradox of the court begins, because both men believe they must win, no matter the verdict. Protagoras argued, "If I win this case, the court will compel you to pay me, and I get my fee. But if I lose, then you've won your first case, and per our agreement, you must pay me. Either way, I should be paid." Euathlus, however, countered with a twist. "If I lose this case, then by the terms of our agreement, I haven't yet won a case, so I owe you nothing. But if I win, the court will say, I don't have to pay you, so in either outcome, I shouldn't have to pay." This clever legal entanglement creates a paradox, a loop of logic where both parties can argue they win, regardless of the court's decision. It highlights the strange tension between formal contracts and legal outcomes, between the letter of an agreement and the judgment of a court. The paradox has fascinated legal scholars for centuries, not just for its wit, but for its real implications about how rules are interpreted. The paradox of the court reveals how justice, when tied too tightly to logic without room for context, can fold in on itself. It reminds us that truth and fairness sometimes lie not in clever arguments, but in the deeper intentions behind them. Grandfather paradox. Imagine you discover a time machine, and with it the ability to travel to the past. Curious and bold, you journey back several decades, perhaps even a century. There you find your grandfather as a young man, long before he ever met your grandmother. And then, For some reason, perhaps by accident, perhaps by intent, the question then becomes chillingly clear. If your grandfather never lived to have children, then one of your parents was never born. And if your parent was never born, then neither were you. But if you were never born, then how did you travel back in time to stop your grandfather in the first place? This is the grandfather paradox, a classic time travel dilemma that shakes the very foundation of causality. At its heart, the paradox reveals a contradiction in the fabric of cause and effect. You can't be the cause of an event that erases your own existence, because then you would no longer be able to cause it. It creates a loop of impossibility where your actions in the past prevent the conditions that made those actions possible in the first place. It's not just a story device, it's a deep philosophical problem about time, identity, and the logic of sequence. Physicists and philosophers have offered several ways to approach the paradox. One is the idea of self-consistency, that the universe somehow prevents paradoxes from occurring. You might try to stop your grandfather, but events would always conspire to stop you, ensuring the timeline remains intact. Another possibility is the multiverse theory, where any change to the past creates a branching reality. In one universe, your grandfather lives and you're born. In another, he doesn't, and you never exist. The grandfather paradox reminds us that time, though it feels linear and stable, might hold deeper contradictions when bent too far. It asks not just what happens when we travel through time, but whether we ever truly can. Bootstrap paradox. Imagine a young composer discovers a beautiful piece of music. Captivated, they decide to perform it and eventually publish it as their own. Years later, someone travels back in time with a copy of that same music and gives it to the young composer, who then learns it, performs it, and publishes it. But here's the catch. No one ever originally composed the music. It was passed from future to past in an endless loop, with no true point of creation. This is the bootstrap paradox, a time travel riddle that forces us to question the very nature of origin, authorship, and causality. An object, idea, or piece of information exists because it is passed through time by itself, creating a circle with no beginning and no end. The paradox gets its name from the expression, pulling oneself up by one's bootstraps, a metaphor for achieving something impossible. Just like a person can't lift themselves into the air by tugging on their own boots, information or matter shouldn't be able to create itself. And yet, in the closed loop of the bootstrap paradox, that's exactly what happens. A time traveler brings something into the past, and that thing becomes the source of itself in the future. It defies our understanding of cause and effect, because there is no original cause, just an eternal chain that loops back onto itself. This paradox isn't just a clever story, it presents real challenges in the physics of time travel. If information can be trapped in a causality loop, where does it come from? Who is the true creator? And does it violate the conservation of information or the second law of thermodynamics? The bootstrap paradox suggests a reality where creation doesn't require a beginning, and where some things might exist simply because they always have. It's a haunting reminder that time, when twisted into loops, doesn't just bend our understanding, it unravels it completely. Newcomb's paradox. Imagine you're standing before two boxes. Box A is transparent and contains $1,000, 0 cents. Box B is opaque, you can't see inside, but you're told it contains either $1 million, 0 cents, or nothing at all. You have a choice to make. Take only box B, or take both boxes. Here's the twist. A highly advanced predictor, so accurate it's nearly infallible, has already made a prediction about what you'll choose. If the predictor believed you would take only box B, it placed $1 million, 0 cents inside it. But if it believed you'd take both boxes, it left box B empty. The predictor has never been wrong. And now the boxes are sealed. Your choice is in front of you, and you must decide. This is Newcomb's paradox, a mind-bending dilemma that pits free will against determinism and logic against intuition. On one hand, it seems rational to take both boxes. After all, the contents are already set, Taking both guarantees an extra $1,000, 0 cents, no matter what's in box B. This is the argument from dominance. More is always better. But on the other hand, if the predictor is almost always right, and you choose only box B, you'll likely walk away with $1 million, 0 cents. Your decision isn't just about money, it's about belief. Do you trust the predictor's ability to foresee your actions so perfectly that it has already determined your fate? Newcomb's paradox splits decision theory into two camps. One says you should maximize expected utility and take only box B. The other says you should act based on what's already known and take both. The paradox exposes the strange tension between past and future, between what is fixed and what is freely chosen. At its heart, Newcomb's paradox asks a chilling question. If someone could predict your choices with perfect accuracy, are you truly free to choose at all? Twin paradox. Imagine a pair of identical twins. One stays on Earth, while the other boards a spacecraft and travels at nearly the speed of light to a distant star and back. When the traveling twin returns, something strange has happened. They are younger than their sibling, who remained on Earth. Not just by seconds, but possibly by years. The traveling twin has aged more slowly. This is the twin paradox, one of the most famous and counterintuitive consequences of Einstein's theory of special relativity. It's not a thought experiment about trickery or illusion. It's grounded in the mathematics of time itself. At first glance, the situation seems paradoxical. From the perspective of the traveling twin, couldn't they say it was the Earth that moved away and returned, making their sibling the one who should be younger? That's the heart of the confusion. Special relativity teaches that motion is relative. There's no absolute point of rest. But the paradox is resolved when we realize that the two twins do not experience time symmetrically. The twin on Earth remains in an inertial frame, one that isn't accelerating, while the traveling twin undergoes high-speed motion and, crucially, turns around, experiencing acceleration and deceleration. This break in symmetry is what makes all the difference. Time dilation is a real effect in physics. At high speeds, time literally passes more slowly for those in motion, as seen from the perspective of someone at rest. This has been confirmed through experiments involving atomic clocks flown on aircraft and satellites. The twin paradox isn't just an imaginative riddle. It's a glimpse into the strange, flexible nature of time under the rules of relativity. The paradox reminds us that time is not a universal constant ticking away equally for everyone. It bends, it stretches, and it's deeply dependent on how we move through space. What seems like a contradiction is, in truth, a revelation of how reality defies our everyday expectations when we venture far from the familiar speeds and scales of human life. McTaggart's paradox. Imagine trying to describe time not by numbers on a clock, but by the flow of events, past, present, and future. You say, "The meeting was yesterday, it is raining now, and tomorrow I'll travel." This way of talking about time feels natural, almost essential to how we experience reality. But early 20th century philosopher John McTaggart argued that this flow of time is an illusion. In his famous paradox, he claimed that time as we know it does not exist. What begins as a study of how we talk about time quickly turns into a radical challenge to the very idea of temporal reality. This is McTaggart's paradox, also known as the unreality of time, and it remains one of the most profound and unsettling ideas in the philosophy of time. McTaggart began by distinguishing between two ways we think about time. The first is the A series, which orders events as past, present, or future. The second is the B series, which orders events by their fixed positions, one happening before or after another. McTaggart believed that for time to be real, there must be genuine change, and only the A series allows for change. The B series, though useful for sequencing events, doesn't actually change. It's like a frozen timeline. But here's the paradox. McTaggart argued that the A series is inherently contradictory. He explained that every event must be past, present, and future, but not all at once. A birthday party is future, then present, then past. To describe this transition, we must rely on the A series. But if every event is supposed to have all three properties at different times, we must again rely on time to explain the shift, and thus we're caught in a loop, explaining time with time. This, he said, is incoherent, since the A series is contradictory, and the B series alone cannot account for the passage of time. McTaggart concluded that time itself is unreal. McTaggart's paradox forces us to question whether the flow of time is something real in the world or just a feature of how human minds experience it. And in doing so, it turns the familiar into the strange, revealing time not as a river, but perhaps as an illusion we've never dared to question. Sleeping Beauty problem. Imagine a woman named Sleeping Beauty who agrees to take part in a peculiar experiment. On Sunday, she is informed of the rules. A fair coin will be tossed. If it lands heads, she will be awakened once, on Monday, and then the experiment ends. If it lands tails, she will be awakened twice, once on Monday and again on Tuesday, but with her memory of the first awakening erased. Each time she wakes up, she doesn't know what day it is or whether she's been awakened before. When she wakes up, she's asked one simple question: what is the probability the coin landed heads? This is the Sleeping Beauty problem, a philosophical paradox that confuses even the most experienced thinkers. At first it seems straightforward. The coin is fair, heads or tails, each with a 50% chance. That's what Sleeping Beauty knew going in, but once she wakes up, her situation has changed. If the coin landed heads, there is only one awakening, this one. If it landed tails, there are two awakenings, and this could be either of them. Since she doesn't know which waking this is, some argue she should reason that tails is now twice as likely. That would make the probability of heads 1/3 and tails 2/3. This is the thirder position. Others argue the coin toss itself hasn't changed. It was a fair toss, and waking up doesn't provide new information about whether it was heads or tails. So the probability should remain 50-50. This is the Haffer position. The paradox lies in how we update our beliefs based on uncertain experiences and imperfect memory. It explores deep questions about subjective probability, information, and what it means to be uncertain in a world where experiences can repeat and memory can be unreliable. The Sleeping Beauty problem reminds us that even the most basic concepts, like waking up and asking a question, can become tangled in complex reasoning. And it challenges us to consider how our knowledge, or lack of it, shapes the truths we believe about the world. 2. Watch paradox. Imagine you have two perfectly synchronized watches. You wear one on your wrist, and the other is placed on a high-speed aircraft that travels around the world and returns. When the traveling watch is compared to the one that stayed with you, something surprising appears. It shows less time has passed. The two watches no longer agree. The one that remained on your wrist marks more time than the one that journeyed at high speed. This is the two-watch paradox, a variation of the famous twin paradox from Einstein's theory of special relativity. It seems to present a contradiction. If all motion is relative, why should one watch be younger than the other? At first, this feels confusing. From the perspective of the watch on the aircraft, it could claim that it was the stationary one and the earthbound watch was the one in motion. If all motion is relative, shouldn't both watches experience time in the same way? But the paradox begins to dissolve when we look closely at the paths each watch takes through space-time. The watch that remains on Earth stays in a single inertial frame. It doesn't change direction or speed. The traveling watch, however, accelerates and decelerates as it changes course, breaking the symmetry. According to special relativity, time passes more slowly for objects in motion compared to those at rest, a phenomenon known as time dilation. The faster you move, the slower your clock ticks compared to one that's stationary. But this only holds when the frames of reference are not accelerating. The key to resolving the two-watch paradox lies in the fact that the traveling watch undergoes acceleration and changes direction, making its path through time fundamentally different. The two-watch paradox reminds us that time is not absolute, and motion is not just about speed, but also about the structure of the journey. It teaches us that even two identical timepieces can fall out of sync, not through malfunction, but through the deep and hidden logic of the universe itself. Nowhere now paradox. Imagine trying to point to the exact location of now on a timeline of the universe. You can mark the past, the Big Bang, the birth of the stars, your childhood memories. You can imagine the future, the rising of tomorrow's sun, the ticking of a clock yet to be heard. But now, that elusive instant between what has happened and what has not yet come slips through your fingers. As soon as you try to define it, it vanishes. This is the nowhere now paradox, a haunting reflection on the impossibility of locating the present in any objective, absolute sense. Time, which seems to flow so naturally in our experience, becomes strangely untethered the moment we try to pin it down. In physics, especially in the theory of relativity, there is no universal now. Events that seem simultaneous to one observer may not be simultaneous to another, depending on their motion or position in space. What is happening right now for you could already be past or still future for someone moving at a different speed or standing in a different place. Just as there is no absolute here, there is no absolute now. Yet in everyday experience, now feels undeniably real. It's where your attention lives, where your choices unfold, where life is actually lived. The paradox emerges from this contrast between the subjective experience of a vivid, flowing present and the scientific reality that treats all moments as equally real, equally fixed within the block universe model of time. The nowhere now paradox forces us to ask, is the present a real slice of the universe, or is it merely a trick of consciousness? Are we living in a moving moment, or are we beings who experience one point in a frozen landscape of time? Perhaps now exists not in the world, but only in the mind, a flickering frame in the movie of existence, never seen from outside, but always felt from within. Presentism versus eternalism. Paradox. Imagine standing at the edge of a vast canyon, where the past stretches behind you like layered rock, and the future lies hidden in mist beyond the horizon. You feel the wind, the sun, the present moment. Everything you know exists now. This is the view of presentism, the belief that only the present is real. The past is gone, the future is not yet, and the only true existence is what is happening at this very instant. But now imagine stepping back, floating above the canyon, and seeing the entire timeline of the universe laid out before you, past, present, and future all equally real, coexisting like pages in a book. This is eternalism, the idea that all points in time are equally real, that nothing is truly lost and nothing is ever not yet. The paradox arises when these two views collide, both offering compelling yet contradictory visions of time and existence. Presentism feels intuitive. We experience life one moment at a time, and we talk about the past as memory, the future as possibility. If only the present exists, then we are truly alive only in this single, fleeting instant. But the challenge comes from physics, especially Einstein's theory of relativity, which tells us that simultaneity, the idea that two events happen at the same time, is not universal. What's happening now for one person might be in the past or future for someone else, moving at a different speed or location. In this framework, the universe looks more like a four-dimensional block, where all times exist together. This undermines presentism and supports the eternalist view. Yet eternalism is deeply unsettling. If all times are equally real, then the future is already fixed. Free will becomes questionable. The idea of flowing time dissolves. You are not moving through time. You are just a part of it, like a bead frozen on a string. The presentism versus eternalism paradox asks us to choose between what we feel and what we calculate. Is time a living flame that burns one moment at a time, or is it an unchanging structure, indifferent to our sense of movement? In choosing between them, we may not just be choosing a theory, we may be choosing what kind of universe we believe we live in. Entropy reversal paradox. Imagine watching a glass fall from a table. It hits the ground, shatters into countless pieces, and spreads across the floor in a chaotic pattern. This is entropy in action, the movement from order to disorder, from a neat, whole object to a scattered mess. This process feels irreversible. You never see a shattered glass leap back onto the table and reform itself, but according to the fundamental laws of physics, especially those governing particles and their interactions, the equations work perfectly well in both directions, forward and backward in time. There is nothing on the microscopic level that forbids the reversed motion. So why, in all of our experience, does entropy only seem to increase? Why does time have a direction at all? This is the entropy reversal paradox, a deep and disquieting question about the nature of time, order, and the arrow that seems to push us endlessly forward. Entropy, as defined in thermodynamics, measures the number of ways a system can be arranged, its level of disorder. The second law of thermodynamics tells us that, in an isolated system, entropy tends to increase. This gives rise to what we experience as the arrow of time. Eggs break, memories form, people age, and stars burn out. But if the laws of physics don't favor one direction of time over another, why is entropy always rising and never falling? One possible answer lies in the universe's initial conditions. At the moment of the Big Bang, the universe began in a state of incredibly low entropy, highly ordered, almost impossibly so. From there, disorder has increased. But why did it begin that way? And what would happen if, at some far-flung point in the future, entropy started to decrease? Would time appear to reverse? Would people remember the future and forget the past? The entropy reversal paradox forces us to ask whether the passage of time is a fundamental truth or simply a feature of how we perceive change. It whispers that perhaps time doesn't flow at all, that it's we who drift, like fallen glass, through a one-way cascade of chaos, unable to climb back up to the order we came from. Paradox of the self. Who are you? It seems like a simple question until you start to answer it. Are you your body, your memories, your personality, your name, your voice, your history? The deeper you look, the more slippery the concept becomes. At the heart of this inquiry lies the paradox of the self, the strange and unsettling realization that the thing you call I may not be a thing at all. You are the subject of your own experience, the narrator of your life story, yet when you turn attention inward to find the source of that voice, it vanishes. The observer cannot fully observe itself, and the self that claims to know itself always seems to be one step removed. Philosophers and mystics alike have wrestled with this paradox. When you examine your thoughts, you realize that your thoughts are not you. They come and go, change and evolve. When you observe your emotions, your sensations, your mental images, you begin to see them as events, not as essence. So who, then, is the one observing? Descartes famously said, "I think, therefore I am," grounding the self in the act of thought. But even thought is not always in your control. It arises unbidden, like weather in the mind. If you are not your thoughts, nor your body, nor your memories, what remains? Some traditions suggest that the self is an illusion, an emergent property of the brain, a construct created by language and society. Others propose that the self is a process, not a thing, something that unfolds in time, shaped by relationships, choices, and attention. And still others claim that the self is a deeper consciousness beyond personality, something hidden behind the mask of daily identity. The paradox of the self is not meant to be solved, it is meant to be lived with, questioned, turned over like a coin in the palm of your hand. It reminds you that even the most familiar experience, being you, is a mystery deeper than certainty, and perhaps, in that mystery, there is something quietly true, that you are not just a person, but a question the universe keeps asking. Theseus's memory ship. Imagine not a wooden ship sailing through oceans, but a vessel made of memories, your memories. Picture your mind as the ship of Theseus, sailing across the sea of life. Along the way, some memories fade, weathered by time. Others are replaced, reinterpreted, edited, or even forgotten. New experiences take their place, reshaping who you think you are. Yet at every moment, you still feel like you. This is the paradox of Theseus' memory ship, a thought experiment that explores identity not through physical parts, but through the fragile, shifting pieces of memory. If all your memories were replaced one by one, would you still be the same person? If you forgot every childhood moment, every friendship, every love, every loss, what would remain of you? Is memory the anchor of identity, or merely its record? And if memory is not reliable, if it fades, lies, or rewrites the past, then how stable is the self that leans on it? Just like the planks of Theseus's ship were gradually swapped out, our sense of self evolves with every moment remembered and every detail forgotten. But when does change become transformation, and at what point does transformation become replacement? Now imagine this. Someone builds a replica of your younger self using your original memories, your old journals, home videos, digital footprints, and stories from those who knew you. This new version feels like you, acts like you, and remembers everything you once did. Meanwhile, the current you continues forward with new experiences and memories that the replica does not share. So who is the real you? The one who remembers your past, or the one who was there but no longer remembers? Theseus's memory ship reminds us that we are not fixed structures, but ongoing narratives, ships rebuilt in every moment we remember or forget. Identity may not be something we possess, but something we constantly reconstruct. And if we are our memories, then we are also the silences between them, the missing planks, the faded pages, the forgotten names. The inverted spectrum. Imagine two people looking at the same ripe strawberry. Both say it's red, both agree it's not green or blue, and both stoplights and sunsets appear just as they should. But what if, deep inside, the color experience, what philosophers call qualia, is completely different between them? What if, for one person, red feels like what the other experiences as green, even though they both use the same word and behave the same way? This is the inverted spectrum, a paradox that questions whether we can ever truly know what another person's experience feels like from the inside. It challenges the limits of language, science, and empathy. The paradox begins with a simple premise. Behavior and language can remain perfectly identical even if inner experiences differ. If person A sees red and calls it red, and person B sees what we would call green but also calls it red, how could we ever know? Their brains function normally, their reactions are the same, and their vision passes every test. But their inner worlds could be inverted. The strawberry to one might be the sky to another, and neither would ever suspect the difference. There is no external way to measure qualia, the subjective quality of experience. You can't point to a color and prove how it feels. This thought experiment doesn't rely on any malfunction or deception. It doesn't say anyone is wrong. In fact, it works precisely because no one can be proven right. It forces us to ask whether consciousness is purely physical, or if there's something more, something private and irreducible to behavior or biology. The inverted spectrum reminds us that experience is not always accessible from the outside. It suggests that there may be an unbridgeable gap between minds, that even in perfect agreement, we may still live in parallel but unseen worlds. And in that space, we're left wondering, how well can we ever know another person's reality when we can't even be sure we share the same colors? The Chinese room argument. Imagine a man locked inside a room. He doesn't speak Chinese, not a word, but inside the room he has an enormous rulebook written in his own language. Through a small slot, someone outside slips in a piece of paper covered in Chinese characters. The man doesn't understand it, but he consults the rulebook, which tells him exactly how to match the symbols, how to respond, and what to send back. He copies the response and slips it out. To the person outside, it seems as though the man understands Chinese. The answers are coherent, relevant, and fluent. But does the man actually understand anything? Or is he just manipulating symbols with no comprehension? This is the Chinese room argument, a famous thought experiment by philosopher John Searle, designed to challenge the idea that artificial intelligence can truly understand language. The room represents a computer, the man is the CPU, the rulebook is the program, the input and output are language. According to this model, the computer passes the Turing test. It behaves in a way indistinguishable from a human. But Searle argues that this behavior isn't proof of consciousness or understanding. The system has syntax but not semantics. It follows rules, but it doesn't know what the symbols mean. It gives the illusion of intelligence, but lacks any inner awareness or comprehension. Supporters of strong AI argue that understanding emerges from the system as a whole. Even if the man doesn't understand, perhaps the room, the entire process, does. But Searle insists that genuine understanding requires more than function. There must be something inside that knows, something that experiences meaning, not just processes it. The Chinese room argument forces us to question what we mean by thinking. Is intelligence just behavior? Is understanding just pattern recognition? Or is there something irreducibly conscious about the mind? Something machines, no matter how advanced, may never replicate. It's a quiet whisper behind every smart device and chatbot. Are these systems truly intelligent? Or just clever rooms, forever sealed, mimicking thought without ever thinking at all? Swamp Man thought experiment. Imagine you're walking alone through a remote swamp. A sudden lightning bolt strikes you dead instantly, your body obliterated beyond recognition. At the same time, by sheer cosmic coincidence, another lightning bolt strikes a nearby patch of water and spontaneously assembles, atom by atom, an exact replica of your body, down to the very last detail. This creature, called Swamp Man, stands up, breathes, blinks, and walks out of the swamp thinking it's you. It remembers your past, recognizes your friends, speaks your language, and continues your life seamlessly. But here's the question. Is Swamp Man really you? And more disturbingly, does it even have a mind? This is the Swamp Man thought experiment, proposed by philosopher Donald Davidson, and it challenges everything we believe about identity, meaning, and consciousness. From the outside, Swamp Man behaves exactly like you. It remembers your childhood, your favorite songs, your fears and dreams, but it was never born. It never had parents. It never formed memories from experience. Its knowledge and personality are not earned through interaction with the world, they're copied by accident. So can it really mean anything it says? Can it understand what it thinks it knows? Or is it just a hollow echo of a person? Some philosophers argue that Swamp Man is fully conscious and self-aware. If its brain is identical, its mind must be too. Others insist that meaning depends on causal history, on real experiences and relationships that connect a person to the world. Without that history, Swamp Man's thoughts and words might be empty, like a mirror with no reflection of its own. The Swamp Man forces us to confront what makes you truly you. Is it your structure, your memories, your history, or is there something deeper? A soul, perhaps, or a personal thread that lightning can't replicate. In the quiet reflection that follows this thought experiment, we're left wondering, are we the sum of our parts or the sum of our past? And if something walks and talks like us but was never born, does it belong in the story it remembers, or is it only pretending to be someone who's already gone? Parfit's teletransportation problem. Imagine stepping into a futuristic teletransporter, ready to travel from Earth to Mars. The machine scans your entire body, every atom, every neuron, every memory, and transmits that information at light speed to a receiver on Mars. There, another machine reconstructs your body atom for atom, creating an exact replica, with all your thoughts, memories, and personality intact. The moment the process is complete, this new version of you wakes up on Mars, thinking, I made it. But here's the haunting question. Did you really survive the journey, or did you die, and a perfect copy took your place? This is Parfit's teletransportation problem, a powerful and unsettling thought experiment from philosopher Derek Parfit. It explores the nature of personal identity and continuity, what it really means to be you over time. If the person on Mars thinks, feels, and remembers everything you do, isn't that enough? Or is there something more required, some non-physical thread of continuity that didn't make the trip? Some argue that the copy is you. If the mind and body are identical, if the memories and personality are preserved, then identity has simply been transferred. After all, we already replace the atoms in our bodies gradually throughout our lives, and we still consider ourselves the same person. But others resist this conclusion. They say that what matters is not just the information, but the process, the continuous chain of existence. And in this case, the original body is destroyed. That break, they say, is the end of the original you. Parfit pushed this further. Suppose the machine malfunctions and the original you isn't destroyed. Now there are two of you, one on Earth, one on Mars. Which one is the real you? Can both be? Or does personal identity begin to lose meaning in a world where copies can be made? Parfit's teletransportation problem doesn't just ask whether we survive a trip to Mars. It asks what we are to begin with. A body? A pattern? A story? And if that story can be perfectly replicated, perhaps survival isn't about remaining the same person, but about ensuring that someone like you continues to exist, even if the original is left behind in the static of transmission. Split brain paradox. Imagine a person undergoing a radical surgical procedure that severs the corpus callosum, the bundle of nerve fibers connecting the two hemispheres of the brain. This operation is real. It's been used to treat severe epilepsy. Afterward, the two sides of the brain can no longer communicate directly. The result is a split brain patient, one body, one face, one voice, but perhaps two separate minds. In carefully designed experiments, scientists discovered something strange. If you present an image to the right visual field, processed by the left hemisphere, the person can name it. But if the image is shown only to the left visual field, processed by the right hemisphere, the person says they see nothing, even though their left hand can point to the correct object. One hemisphere knows, but cannot speak. The other can speak, but doesn't know. This is the split brain paradox, a startling challenge to our understanding of consciousness and personal identity. We often assume we are one unified self, a single I observing, thinking, deciding. But the split brain suggests that this unity may be an illusion. If the two hemispheres can hold different beliefs, make different decisions, and even appear to have different desires, which one is you? Or are both you? What happens when your left hand starts unbuttoning your shirt while your right hand buttons it back up, as some patients report? Are you witnessing a civil war within your own mind? The paradox forces us to ask whether consciousness is indivisible or modular. Is it possible to have two centers of awareness in the same skull? If so, does splitting the brain split the self? Or was there never just one self to begin with, only a collaboration between different cognitive systems, loosely stitched together by memory and language? The split brain paradox shakes the very foundation of identity. It hints that what we call the self may be more fragile, more fractured, more distributed than we imagine. And in that silent divide between hemispheres, we find the haunting possibility that the unity of consciousness is not a fact, but a feeling. Brain in a vat. Imagine waking up one day and being told a shocking truth. Your entire life, your memories, sensations, thoughts, and beliefs has all been an illusion. In reality, your brain is sitting in a vat of nutrients in a laboratory, connected by wires to a powerful computer. Every experience you think you've had Walking, eating, falling in love, seeing sunsets is just electrical signals fed into your brain by a machine. You were never born, never touched the ground, never saw the sky. This is the brain in a vat thought experiment, a modern twist on Cartesian skepticism that asks, how do you know that anything you experience is real? The paradox is not about technology or science fiction, it's about certainty. Can you ever truly prove that your reality is not simulated? If your brain receives all the same signals it would receive in the real world and you respond as if they're real, then what's the difference? The brain in the vat believes in its world just as you believe in yours. It feels hunger, joy, confusion, even doubt, and yet it floats alone, isolated from everything it thinks it knows. So how can any of us be sure we're not just brains in vats? Philosophers use this thought experiment to explore the limits of knowledge and the relationship between mind and world. If perception is our only window to reality, and perception can be simulated, then what guarantees the world we see is genuine? Some argue that we can't know for certain. Others suggest that it doesn't matter. If experience is all we have, then even a simulated life is still our life. The brain in a vat doesn't try to convince you that your world is fake. It simply asks how you know it's real. And in that question, it opens a quiet void beneath our certainty, inviting us to wonder, what is reality if we can never step outside our own mind to see it for sure? Problem of other minds. You watch someone smile. They laugh, nod, speak with warmth in their voice. You assume they feel joy, just like you would in their place. But do you truly know they're experiencing anything at all? You can see their behavior, hear their words, read their expressions, but you cannot enter their mind. You cannot feel their feelings. This is the problem of other minds, a deep philosophical puzzle that asks, how can we be certain that anyone besides ourselves has consciousness, emotions, or subjective experiences? At first, it seems like a strange question. Of course, other people are conscious. We talk to them, live with them, love them. But the paradox isn't about social experience, it's about epistemology, the limits of what we can know. You know your own mind directly, you feel pain and happiness, you reflect. But for everyone else, you must infer. You assume their minds exist because they behave as if they do. But behavior is not proof of awareness. A robot might smile and speak, a puppet might weep on command. Could the people around you simply be well-programmed machines, philosophical zombies, doing everything a conscious being would, but with no inner life? Some philosophers argue that this skepticism is unwarranted. We have no reason to doubt other minds if they act like ours. Others, like solipsists, suggest we can never be sure anyone else exists at all. The paradox becomes especially poignant in cases where awareness is uncertain, in babies, in coma patients, or in artificial intelligence. If we can't see consciousness, how do we recognize it? The problem of other minds doesn't accuse the world of being empty, it simply reveals how alone we are in our own experience. We live surrounded by minds we cannot touch, by feelings we cannot verify, and yet we reach for each other anyway, building meaning not through certainty, but through trust. Because perhaps what binds us together is not proof of awareness, but the shared mystery of being human. Paradox of personal identity. Imagine a child staring at their reflection in a pond, innocent and curious. Now imagine that same person decades later, older, weathered, filled with memories and regrets. Are they still the same person? On paper, yes. Legally, biologically, perhaps. But psychologically, emotionally, experientially, so much has changed. This is the paradox of personal identity, a question that haunts philosophy, psychology, and everyday life. What makes you, you? And if everything about you can change over time, then what, if anything, remains constant? At first glance, we assume identity is continuous. You are the same person who went to school, who made mistakes, who once cried over a lost toy. But memories fade, desires shift, cells die and regenerate, beliefs, personalities, and even values evolve. The you of today might barely resemble the you of 10 years ago. So where is the thread of continuity? Is it your body, your name, your mind, or something else entirely? Some philosophers argue that memory is the glue of identity. You are the same person because you remember being that person. But memory can be unreliable, fragmented, even false. Others suggest it's the persistence of the body or the brain, but even those change constantly. Split brain cases, neurological damage, and personality-altering traumas all blur the line between continuity and transformation. And in extreme cases like amnesia, does identity survive when memory is gone? The paradox deepens when we think about teleportation, mind uploading, or even identical twins. If a perfect copy of your body and brain were made, down to the last synapse, would that be you? If you changed every part of yourself, gradually, without noticing, would you ever stop being you? The paradox of personal identity doesn't offer easy answers. It invites you to reflect on the illusion of permanence, the quiet erosion of sameness, and the strange possibility that the self is not a fixed entity but a flowing process. Perhaps we are not who we once were and not yet who we will be, but something moving in between, shaped by time, memory, and the stories we choose to believe. Monty Hall problem. Imagine you're on a game show standing before 3 closed doors. Behind one of them is a brand new car, behind the other 2, goats. You don't know which is which. You choose door 1. The host, Monty Hall, who knows what's behind each door, smiles and opens door 3, revealing a goat. Then he turns to you and asks, would you like to switch to door 2 or stick with your original choice? At first glance, it feels like it doesn't matter. 2 doors remain, one with a car, one with a goat. Isn't it a 50-50 chance now? This is the Monty Hall problem, a famous probability paradox that tricks even the sharpest minds. The surprising answer? You should always switch. Why? Because the odds are not 50-50. They're 1 in 3 if you stay, and 2 in 3 if you switch. When you first pick a door, you have a 1/3 chance of choosing the car, and a 2/3 chance that the car is behind one of the other 2 doors. Monty always opens a door with a goat. He never reveals the car. That's key. So if you initially chose wrong, which happens 2 out of 3 times, Monty's action effectively reveals the correct door by process of elimination. Switching wins in those 2 out of 3 cases. The Monty Hall problem is so counterintuitive that even mathematicians and statisticians have struggled with it. It violates our gut feeling of fairness and symmetry. We think removing one losing door makes the odds even, but the host's knowledge and behavior skew the probabilities. His choice isn't random, it's informed, and that changes everything. This paradox doesn't just teach us about probability, it humbles us. It reminds us that intuition often fails in the face of logic, and that the truth, even when explained, can feel wrong. The Monty Hall problem invites us to question how we make decisions, and to remember that the right answer might be hidden behind the door we almost didn't choose. Bertrand's box paradox. Imagine 3 identical boxes, each containing 2 coins. One box holds 2 gold coins, another holds 2 silver coins, and the third contains 1 gold and 1 silver. You pick a box at random and draw 1 coin. It's gold. Now here comes the question. What's the probability that the other coin in the same box is also gold? At first it might seem like a simple 50-50 choice. Either you're holding the mixed box or the all-gold box. But the answer, surprisingly, is not 1/2. It's 2/3. This is Bertrand's box paradox, a classic puzzle in probability theory that reveals just how easily our intuition can be fooled. Let's slow it down. There are 3 boxes, GG, 2 gold, SS, 2 silver, and GS, 1 gold, 1 silver. When you draw a gold coin, you eliminate the SS box. So you're now left with 2 possible boxes, GG and GS. But here's the twist. you're more likely to have drawn that gold coin from the GG box than the GS box. Why? Because the GG box has 2 gold coins, while the GS box only has 1. So out of all the possible gold coins you could have drawn, 2 came from GG and only 1 came from GS. That's a total of 3 possible gold coins, and 2 of them belong to the all-gold box. So the probability that you're in the GG box, given that you drew a gold coin, is 2 out of 3. That makes the chance that the other coin in the box is gold also 2/3, not half. Bertrand's box paradox shows how the structure of a problem, what information is revealed, and how can quietly distort our sense of likelihood. It reminds us that probability isn't just about the number of outcomes, but about how those outcomes are weighted by the circumstances. It's a quiet lesson in humility. What feels obvious often isn't, and certainty sometimes hides in the place we least expect. Simpson's paradox. Imagine you're comparing 2 treatments for an illness. Treatment A seems to work better for men, and it also works better for women. Naturally, you conclude that treatment A is superior overall. But when you look at the combined data, men and women together, something astonishing happens. Treatment B comes out ahead. How can that be? How can a treatment be better in every subgroup, yet worse in the total? This is Simpson's paradox, a statistical illusion that challenges how we interpret data, revealing how the truth can reverse itself when we stop looking closely. The paradox occurs when a hidden variable, called a confounding factor, distorts the results. In the treatment example, it might be that treatment A was mostly given to very sick patients, while treatment B was given to those with mild symptoms. So, within each group, men and women, treatment A performed well, but the distribution of patients skewed the combined numbers, making treatment B appear better. The result? A reversal that seems logically impossible but is statistically sound. This paradox shows up everywhere, from medical studies to university admissions to criminal justice. In one famous real-world case, a university was accused of gender bias in graduate admissions. The overall numbers suggested women were admitted at lower rates, but when the data was broken down by department, it turned out women had applied in greater numbers to the most competitive programs. In most departments, they were actually admitted at higher rates than men. Simpson's paradox doesn't just demonstrate a mathematical curiosity, it warns us that data without context can mislead. Patterns can reverse when viewed through different lenses. The truth can hide behind averages, waiting for someone to ask the right question. In a world driven by statistics, the paradox reminds us that numbers alone are not enough. We must always look beneath them, asking, what's missing? What's hidden? And are we seeing the full story or just the most convenient one? Birthday paradox. Imagine walking into a room filled with strangers. You glance around, thinking, what are the odds that 2 of us share the same birthday? With 365 days in a year, it seems unlikely, maybe only in a big group, you think. But here's where the mind bends. In a room of just 23 people, there's a better than 50% chance that 2 of them share the same birthday. This is the birthday paradox, a famous probability puzzle that reveals how human intuition fails when it comes to randomness and combination. At first, the logic feels off. How can such a small group create such a high chance of overlap? The trick lies in the number of possible pairs. You're not comparing your birthday to everyone else's, you're comparing everyone to everyone else. In a group of 23 people, there are 253 unique pairs. That's 253 opportunities for a shared birthday. And with each new person added to the room, the number of comparisons grows rapidly. We tend to underestimate the cumulative power of pairwise combinations. Our minds focus on direct, one-to-one comparisons, my birthday versus yours. But probability doesn't work that way in groups. Instead, it multiplies the possibilities, creating surprising outcomes from seemingly small samples. The counterintuitive result: by the time there are 57 people in the room, the chance of a shared birthday climbs to over 99%. The birthday paradox doesn't rely on leap years or specific dates. It's purely about probability. It's not that birthday coincidences are magical, but that our minds are wired to misunderstand how often they should happen. This paradox is a gentle reminder that reality often behaves differently than we expect, that chance can hide in plain sight, and that in the randomness of life, what seems improbable might just be quietly inevitable. Boy or girl paradox. Imagine a family has two children. You're told that one of them is a boy. What are the chances that both children are boys? At first, the answer feels obvious. There are two kids, and one is a boy, so the other must have a 50% chance of being a boy too, right? That's the intuitive response. But the real answer is 1 in 3, not 1 in 2. This is the boy or girl paradox, a seemingly simple probability puzzle that reveals how carefully we must define what we know before making assumptions about what we don't. Let's break it down. There are 4 equally likely combinations for 2 children. Boy and boy, boy and girl and boy, girl and girl. But if we know at least one child is a boy, we can eliminate the girl and girl scenario. That leaves us with 3 possibilities. Boy and boy, boy and girl and boy. Only one of those combinations includes 2 boys, so the probability that both children are boys is 1 out of 3. But the paradox deepens depending on how the information is presented. If you're told the older child is a boy, then the combinations are restricted by birth order, and the chance that both are boys becomes 1 in 2. Small differences in how a situation is framed can change the entire outcome. That's the real power and the real trick of the paradox. The boy or girl paradox teaches us that probability isn't just about math, it's about context, interpretation, and hidden assumptions. It reminds us that even the simplest questions can contain layers of ambiguity, and that behind every intuitive answer may lie a deeper, more careful truth. In the world of chance, what you know and how you know it can change everything. Parendo's paradox. Imagine playing 2 games. Game A is simple. You flip a biased coin that causes you to lose money more often than you win. It's a losing game. Game B is more complicated. It switches between 2 coins depending on your current amount of money. One coin is heavily biased against you, and the other is only slightly favorable. On its own, Game B is also a losing game. So you might reasonably conclude that playing either game will drain your fortune over time. But here's the surprise. If you alternate between the 2 games in a specific sequence, or even randomly, you start winning. 2 losing strategies, combined in the right way, create a winning outcome. This is Parendo's paradox, a stunning twist in probability theory that defies our expectations about chance, risk, and reward. The paradox is named after Spanish physicist Juan Paredondo, who developed it to illustrate principles in statistical mechanics. At its heart, it challenges a deeply intuitive belief that combining failures should only lead to more failure, but in the right configuration, negative trends can interfere with each other and give rise to positive results. It's like 2 opposing forces that, when staggered just right, cancel out each other's weaknesses. Parendo's paradox isn't just a curious game, it has real-world analogies. In economics, for instance, alternating between 2 risky investments might yield better long-term returns than sticking to one. In biology, random fluctuations in environment or strategy can sometimes give rise to stability and growth. Even in social dynamics, alternating between firm and flexible policies may lead to better outcomes than either extreme. The paradox forces us to reconsider what it means to lose, to risk, and to strategize. It reminds us that failure isn't always linear, and that sometimes, paradoxically, the path to success winds through carefully choreographed losses. In the strange world of chance, the whole can be greater and more hopeful than the sum of its parts. 3 prisoners, problem. Imagine 3 prisoners. A, B, and C, awaiting execution. One of them will be pardoned, but none of them knows who. Prisoner A, desperate for hope, asks the warden if he can at least tell him the name of one of the other prisoners who will be executed. The warden, thinking it harmless, says, B will be executed. Now A feels relieved. He reasons, since one of the three will be pardoned and it's not B, then the chance of it being between himself or C must now be 50-50. But has A's probability of survival really improved just because he knows B's fate? Surprisingly, the answer is no. This is the three prisoners problem, a lesser-known cousin of the Monty Hall problem, and it shows how new information can distort our understanding of probability. Initially, A had a 1 in 3 chance of being pardoned. That hasn't changed. The warden's answer, though informative, wasn't random. He would never say A's name to A, so his choice was limited. If A is the one being pardoned, the warden had a choice between naming B or C. But if either B or C is being pardoned, the warden has no choice. He must name the other prisoner. So in most of the possible scenarios, A is still unlikely to be the one who survives. Here's the breakdown. If A is pardoned, the warden could say either B or C. If B is pardoned, 1/3, the warden must say C. If C is pardoned, 1/3, the warden must say B. So the fact that he says B will be executed is more likely to occur in the scenario where C is the one pardoned, making A's odds of being spared still just 1 in 3, while C's chances effectively rise to 2 in 3. The three prisoners problem reminds us that not all information is created equal. What seems like a neutral detail may hide deeper probabilities and unspoken constraints. In the world of uncertainty, even a simple name can quietly shift the odds. St. Petersburg Paradox. Imagine a game with a simple setup and an astonishing promise. You flip a fair coin. If it lands heads on the first toss, you win $2.00. If the first heads comes on the second toss, you win $4.00. If it comes on the third, you win $8.00, and so on, doubling the payout with every extra toss. The rules are clear. The payout is $2.00. N, where N is the number of the toss that gives the first heads. Now, suppose you're asked, how much would you pay to play this game? $10, $100, $1,000? Mathematically, the game's expected value is infinite, but almost no one would pay more than $20.00 or $30.00 to play. This is the St. Petersburg Paradox, a classic puzzle in probability and economics that exposes the strange gap between mathematical value and human intuition. Let's break it down. The probability of the first heads occurring on the first toss is 1/2, and the payout is $2.00. On the second toss, the chance is 1/4, and the payout is $4.00. On the third toss, the chance is 1/8, payout $8.00, and so on. Each term contributes a value of 1 to the expected payout, 1/2 x 2, 1/4 x 4, 1/8 x 8, and since this continues infinitely, the total expected value of the game grows without bound. It seems you should be willing to pay any amount to play, but in practice, people are only comfortable wagering modest sums. The paradox highlights the limits of using expected value alone to make decisions. It introduced the need for utility theory, the idea that the value of money decreases as you gain more of it. A poor person might value a $100.00 gain much more than a billionaire would. That subjective experience of value or utility flattens the curve and makes the game's real-world appeal far more reasonable. The St. Petersburg Paradox reminds us that humans are not abstract calculators. We weigh risk, emotion, context, and diminishing returns. And it's in those imperfections, in that distance between number and need, that our true reasoning lives. Banach Tarski, Paradox. Imagine holding a solid ball in your hand. Perfect, smooth, unbroken. Now imagine that you can take this ball, cut it into a finite number of pieces, and rearrange those pieces to form two identical copies of the original ball. Not crushed or stretched, just reassembled. No trickery, no illusion. From one ball, you now have two. This is the Banach-Tarski paradox, a shocking result in mathematics that defies our physical intuition and challenges our very understanding of space, volume, and reality. At first glance, it seems like a magic trick, or worse, a mistake. But the paradox is a proven theorem in set-theoretic geometry, discovered by Stefan Banach and Alfred Tarski in 1924. It states that a solid sphere in three-dimensional space can be split into 5 non-overlapping pieces, which, through rotation and translation alone, can be reassembled into 2 solid spheres, each identical in size to the original. It seems to violate the conservation of volume. How can you create more matter from nothing? The answer lies in the nature of the pieces. They are not like puzzle pieces you can hold or visualize. They are abstract, infinitely complex, and non-measurable, meaning they don't have a well-defined volume in the traditional sense. The Banach-Tarski paradox relies on the axiom of choice, a controversial principle in mathematics that allows for the selection of elements from infinitely many sets, even when no specific rule for selection is defined. This axiom is essential for the paradox to work, but it also leads to outcomes that feel impossible in the real world. Of course, you can't actually perform the Banach-Tarski construction with real objects. It's purely theoretical. The paradox doesn't apply in the physical universe, because it requires perfect continuity and infinite precision, things that atoms and molecules simply don't allow. But as a thought experiment, it's profound. The Banach-Tarski paradox reveals that the rules of mathematics, when extended into the realm of the infinite, can diverge wildly from the rules of physical reality. It reminds us that even the most grounded concepts, like size, shape, and substance, can be turned inside out by the strange logic of the infinite. Trolley problem. Imagine a runaway trolley racing down a track. Ahead, 5 people are tied to the rails and cannot escape. You stand next to a lever. If you do nothing, the trolley will continue on its path and kill all 5. But if you pull the lever, the trolley will divert onto another track, where a single person is also tied down. You're faced with an impossible choice: do nothing and let 5 die, or intervene and cause the death of 1. This is the trolley problem, one of the most iconic and unsettling thought experiments in moral philosophy. It forces you to confront the question: is it better to passively allow harm, or to actively cause less harm? At first glance, many people say they would pull the lever. Sacrificing 1 to save 5 seems logical. It maximizes lives saved. This is a utilitarian view, focused on outcomes and the greater good. But others hesitate. They feel an unease about becoming the direct agent of someone's death. Even if the numbers favor intervention, the moral weight of causing a death seems heavier than allowing one to happen. That hesitation reveals a deontological instinct, one rooted in rules, rights, and duties, regardless of outcome. Philosophers have pushed the dilemma further. In a famous variation, instead of pulling a lever, you're standing next to a large man on a footbridge above the tracks. The only way to stop the trolley is to push him off the bridge, using his body to stop the trolley and save the 5. Most people now recoil. Though the math is the same, 1 life for 5, the emotional and moral terrain feels radically different. Why is pulling a lever acceptable, but pushing a person is not? The trolley problem doesn't offer answers. It reveals us, our values, our contradictions, our discomfort with moral clarity. It asks not just what you would do, but what you can live with doing. And in that quiet moment before the decision, it shows how ethics is rarely clean, and how even the right choice can still feel deeply, painfully wrong. Fat Man variation. Imagine the trolley is hurtling down the tracks again, just like before, but this time, there's no lever. You're standing on a footbridge overlooking the tracks, and beside you stands a large man. Below, 5 people are trapped and certain to die if the trolley continues. But here's the twist. If you push the man off the bridge and onto the track, his body will stop the trolley, saving the 5. You, however, will have deliberately caused his death. Do you push him? This is the fat man variation of the trolley problem, and it brings the original paradox into sharper, more personal focus. It replaces mechanical detachment with physical involvement and forces you to grapple with the weight of direct moral responsibility. At first glance, the setup seems nearly identical to the classic version. 1 life to save 5. The utilitarian logic is still there. Minimize harm, maximize lives saved. But this version feels profoundly different. Pushing the man requires your hands. It requires intention. It's not redirecting a machine, it's using a person as a means to an end. And that's where many people draw a moral line. This variation highlights a central tension in ethics. Is it ever morally acceptable to sacrifice 1 life to save many, if doing so means using a person as an instrument? Deontological ethics, especially the philosophy of Immanuel Kant, says no. People must be treated as ends in themselves, never as tools. In this view, pushing the man off the bridge violates his autonomy and dignity, even if it saves more lives. The act itself becomes immoral, regardless of the result. The fat man variation makes that tension visceral. It moves the dilemma from abstraction to confrontation. This thought experiment doesn't solve the problem. Instead, it deepens it. It asks, are we responsible for what we do or for what we allow? Does moral worth lie in outcomes or in actions? And what does it say about us when we're willing to pull a lever but not to touch a life directly, even when the stakes are the same? Bystander effect, paradox. Imagine you're walking down a quiet city street at dusk, and you hear a cry for help coming from a nearby alley. You pause, you're concerned, but you notice something. There are several other people around. Some glance toward the noise, some slow down, but no one moves. You assume someone else will help. Maybe they've already called for assistance, maybe it's not serious. So you keep walking. Everyone else does the same, and the person in the alley remains alone. This is the bystander effect paradox, a disturbing contradiction in human behavior, where the presence of more people makes each individual less likely to help. The more potential rescuers there are, the fewer actually act. The paradox lies in the expectation. Logic suggests that with more people present, the chances of someone intervening should go up, but the opposite often occurs. Responsibility becomes diluted. Each person thinks, someone else will do it, or waits for social cues to validate whether the situation is serious. As a result, no one steps forward. Psychologists have confirmed this effect in numerous experiments. When people believe they are alone, they are more likely to help. When others are present, even strangers, they hesitate. The bystander effect forces us to question the relationship between collective presence and personal duty. It reveals that awareness of others doesn't always amplify compassion, it can suppress it. We tend to act not only based on what's right, but on what others appear to be doing. And when everyone is waiting for someone else, no one moves. This paradox isn't just about emergencies. It shows up in workplaces, in classrooms, in digital spaces, anywhere people think someone else will take responsibility. And it whispers a hard truth. The more we blend into the crowd, the easier it becomes to forget that we are the crowd. The bystander effect paradox reminds us that moral responsibility doesn't scale with numbers, it sharpens with presence. And sometimes, to act ethically means to break from the group, to be the one who steps forward while everyone else is still looking around. Prisoner's dilemma. Imagine you and a friend have been arrested for a crime, but the police don't have enough evidence to convict you both of the worst charge. They separate you into 2 rooms and offer each of you a deal. If you both stay silent, cooperate, you'll each serve 1 year in prison for a lesser charge. If one of you betrays the other, defects, the betrayer will go free, while the other gets 3 years in prison for the full charge. If you both betray each other, you'll both serve 2 years in prison for the full charge. You can't communicate with your partner. What do you do? If you trust them to stay silent, you'll only serve 1 year. But if they betray you, you're stuck with 3 years. If you betray them and they stay silent, you go free. But if you both betray each other, you're each stuck with 2 years. This is the prisoner's dilemma, one of the most famous paradoxes in game theory. At first, it seems that mutual cooperation, both remaining silent, is the best outcome for both. But there's a catch. Both of you have a powerful incentive to betray the other, because defection offers a better personal outcome if you believe the other will cooperate. This self-interested reasoning leads to a paradox. While mutual cooperation benefits both, the rational choice for each person is to betray, even though that leads to a worse collective outcome. The dilemma isn't just theoretical, it's a model for understanding real-world situations where individual interests conflict with collective welfare. It applies to everything from business negotiations to environmental policy, to arms races and international diplomacy. In any situation where cooperation is beneficial, but mistrust makes betrayal seem tempting, the prisoner's dilemma plays out. The paradox challenges the idea that rational self-interest always leads to the best collective outcome. It highlights the tension between short-term gain and long-term cooperation, and it forces us to confront a deeper question. Can we trust each other enough to cooperate, or will we always betray each other, even when it hurts us all? Tragedy of the commons. Imagine a pasture shared by multiple farmers. Each farmer is allowed to let their livestock graze on the land, and each has the same incentive. The more animals they graze, the more profit they make. But as more and more farmers add livestock, the pasture begins to suffer. The grass is overgrazed, the soil depletes, and the land becomes less productive for everyone. If all the farmers acted in their own self-interest, the pasture would eventually be ruined and everyone would suffer. This is the tragedy of the commons, a social dilemma that arises when individuals, acting based on self-interest, deplete or spoil a shared, limited resource, despite the fact that it's in everyone's long-term interest to conserve it. The paradox lies in the clash between individual benefit and collective well-being. Each farmer, seeing a personal gain in adding one more animal, ignores the long-term consequences that affect the group. The tragedy occurs because, although the resource is shared, the cost of overuse is distributed among all users, while the benefits of overuse are enjoyed individually. Even though it would be better for everyone if they limited their livestock, no single farmer has enough incentive to reduce their share. If one farmer cuts back, but others don't, they lose out on potential gains, while the others continue to exploit the land. The tragedy of the commons is not just a theoretical example, it's seen in many areas of life. Overfishing, deforestation, climate change, and the depletion of public goods are all real-world manifestations of this problem. These issues arise when people or organizations exploit shared resources without regard for the future sustainability of those resources. The tragedy shows that individual rationality can lead to collective irrationality. It's a stark reminder that without mechanisms for cooperation or regulation, shared resources are often destined for destruction. The paradox compels us to question how we manage common goods, and whether our individual actions are aligned with the long-term health of our communities and the environment. Paradox of voting. Imagine you're standing in a voting booth, ready to cast your vote for a candidate. It's a simple decision, or so it seems, but then a curious thought occurs. My vote probably won't make a difference. After all, millions of people are voting, and your single vote is just a tiny drop in an ocean. The odds that your vote will change the outcome seem minuscule, and yet, the act of voting feels important, even necessary. This is the paradox of voting, an apparent contradiction between the rational expectation that individual votes don't matter and the widespread belief that voting is a vital civic duty. At its core, the paradox arises from the mismatch between the actual impact of a single vote and the emotional or moral motivation to participate. In large elections, especially in systems with many voters, the probability that your vote will be the deciding factor is so low that it feels practically irrelevant. According to the logic of expected utility theory, the rational decision would be not to vote at all, because the cost of voting, time, effort, etc., outweighs the incredibly small benefit of casting a decisive vote. But people still vote. Why? Because voting isn't purely about the immediate impact of your single vote. It's about contributing to a collective outcome, participating in the democratic process, and expressing a sense of responsibility. People derive satisfaction from the act of voting itself, regardless of the odds of their vote changing the result. There's also a sense of social pressure, or a moral imperative that drives people to vote. After all, democracy only works when people engage. The paradox of voting doesn't just apply to elections. It's a broader reflection of how individuals often act against rational self-interest in favor of collective action, social norms, or intrinsic values. It reminds us that human behavior isn't always driven by cold, calculating logic. Sometimes, the meaning of an action goes beyond its tangible results, existing in the space between personal participation and collective impact. Voting, like many other acts of civic engagement, is a paradox, where the individual's impact is small, yet the act itself carries tremendous societal and psychological significance. Problem of dirty hands. Imagine a politician who, in their quest to bring about change, must make a morally questionable decision. Perhaps they have to approve a corrupt deal to secure vital resources for their country's survival, or maybe they must authorize a military action that results in civilian casualties to protect the greater good. The politician knows these actions are wrong, but they believe the ends justify the means. They are faced with a dilemma. Should they act against their moral principles for the sake of achieving a larger, arguably more important goal? This is the problem of dirty hands, a classic ethical dilemma that challenges the boundaries between morality and political or pragmatic necessity. The paradox arises because, in order to achieve great or necessary outcomes, individuals, particularly those in power, may have to engage in actions that violate their own moral codes. The idea is that, sometimes, the need for effective action in a morally complex world forces people to dirty their hands, to make decisions that would be unacceptable under normal ethical conditions. The politicians' actions, though damaging to their own ethical standing, might be necessary for the well-being of society or the accomplishment of their goals. But the problem of dirty hands is more than just a thought experiment. It raises fundamental questions about leadership, power, and moral compromise. How much moral wrongdoing is acceptable in pursuit of a greater good? Is it possible to achieve a noble goal without compromising one's integrity? And, once you've made such compromises, can you ever justify the harm you've done, or will the stain of your actions follow you forever? Philosophers like Jean-Paul Sartre and Michael Walzer have explored this paradox, and opinions on the matter vary widely. Some argue that leaders must sometimes abandon absolute moral standards in order to act in the best interests of society. Others contend that, by compromising ethical principles, individuals risk losing their legitimacy and moral authority. The problem of dirty hands doesn't offer easy answers. It forces us to confront the tension between ethical purity and the demands of power, reminding us that sometimes doing the right thing may require us to make the most difficult and painful choices. Paradox of deontology. Imagine a situation where a person is forced to make a decision with grave consequences. Let's say there is a runaway trolley and it is headed toward 5 people tied to the tracks. You are standing next to a lever that can divert the trolley onto another track, where one person is tied up. The dilemma: do you pull the lever and actively cause the death of one person to save 5? From a deontological perspective, the right answer is not so clear. Deontologists believe that actions are morally right or wrong based on their adherence to rules or principles rather than on the outcomes they produce. In this case, A deontologist might argue that pulling the lever is morally wrong because actively causing harm, even to save more lives, violates a moral duty to not harm others. This is the paradox of deontology, a conflict between strict moral rules, such as do not kill, and the consequences of breaking those rules in pursuit of a greater good. In this case, the paradox lies in the tension between the deontological duty not to harm others and the consequentialist argument that causing one death to save 5 lives could be justified. According to deontologists, the act of deliberately choosing to end someone's life, no matter the reasoning behind it, violates a fundamental ethical principle. In the deontological view, certain actions are always wrong, even if they lead to better outcomes. This paradox creates a challenge for moral theory. If following a moral rule leads to a worse overall outcome, should the rule still be followed? Can moral duties be suspended in extreme situations? Deontologists like Immanuel Kant argue that morality must be based on universal, absolute rules. Yet, when confronted with real-world moral decisions, the rules can often seem rigid, uncompromising, and out of touch with human experience. The paradox of deontology doesn't provide easy answers. It forces us to question whether moral rules should always take precedence over the outcomes of our actions. Are we morally obliged to uphold these rules, even when they seem to lead to harm? Or is it possible that, in some cases, bending the rules might be justified for the... It's a paradox that shows the complexities of applying ethical principles to real-life situations and how the pursuit of an ideal moral framework can sometimes conflict with the practical realities of human suffering and survival. Paradox of heroism. Imagine a soldier in a battlefield, facing certain danger. He sees an enemy soldier in need of help, pinned under debris. The hero in him rises, and he runs toward the soldier, risking his own life to save the enemy's. He succeeds, but in doing so he exposes himself to the enemy's fire and is gravely injured. In this case, the soldier made a heroic decision, but one that also led to personal harm. The paradox of heroism lies in the contradiction that heroism, by its nature, often requires acts of self-sacrifice and harm for others, but that self-sacrifice can itself be viewed as a moral failure if it leads to needless suffering or death. The paradox begins with the idea of heroism. We admire the person who is willing to put others before themselves, who acts in ways that transcend personal self-interest. A hero is someone who rises above normal expectations of behavior, who defies danger, and who often places themselves in harm's way for the benefit of others. But this very ideal of heroism creates a paradox. If a hero acts to save others at the cost of their own well-being, does that make their action morally admirable or a mistake? Is the hero truly virtuous, or are they just recklessly placing themselves in harm's way, making a poor decision based on misplaced values or emotions? The paradox deepens when you consider that the act of heroism often involves uncertainty. The hero doesn't know whether their sacrifice will even succeed. In many cases, the action could fail, leading not to a glorious rescue, but to failure and possibly greater harm. So, are heroes acting out of courage, or are they acting from a place of moral overreach, where their idealism clouds their judgment? The paradox of heroism doesn't diminish the value of heroic acts, but it highlights a deeper tension. It forces us to ask, can an act of heroism be truly virtuous if it brings harm to the hero? Is it possible that heroism sometimes comes with a hidden moral flaw, one where the good of saving others may not justify the cost to oneself or the wider consequences? This paradox challenges our understanding of heroism, calling us to consider whether true heroism lies not just in selfless sacrifice, but in discerning when to act in the service of others without risking the greater good. It teaches us that sometimes heroism isn't about just doing something grand. It's about knowing when to act with wisdom, not just courage. Paradox of good intentions. Imagine a well-meaning government launches a program to alleviate poverty. They pour millions of dollars into it, and with the best intentions, they aim to provide financial assistance to those in need. However, the program is poorly executed. It inadvertently creates dependency, harms local businesses, and discourages people from finding work. As a result, instead of alleviating poverty, the program deepens the issue. This is the paradox of good intentions, the idea that good intentions alone do not guarantee good outcomes. In fact, sometimes, efforts to do good can lead to unintended harm. At the heart of the paradox is a tension between intentions and consequences. We often justify our actions based on our desire to help others or improve society. However, when the results of those actions are harmful, we are forced to confront a difficult question. Does the good intent behind an action absolve us of responsibility for its negative effects? In many cases, the answer is no. Good intentions, while admirable, don't account for the complexities of reality. When we fail to fully consider the consequences of our actions or the systems we are trying to intervene in, we can unintentionally cause more harm than good. The paradox also reveals a broader issue: unforeseen consequences. Sometimes, the larger systems we are trying to improve are so complex that our well-meaning actions have ripple effects we can't anticipate. This can apply to everything from economic policies, social interventions, to environmental actions. For instance, efforts to protect endangered species might inadvertently disrupt local ecosystems. Environmental policies designed to reduce carbon emissions might have unintended economic consequences, impacting industries and jobs. The paradox of good intentions reminds us that our actions, while motivated by kindness or moral values, can still be flawed or misguided. It challenges us to think critically about the possible outcomes of our decisions and to accept that good intentions do not always translate into good results. It teaches us that being aware of the unintended consequences of our actions is as important as the intentions behind them, and that true wisdom lies in considering both the immediate and long-term effects of what we choose to do. Hilbert's Hotel. Imagine a hotel with an infinite number of rooms, all of them occupied. This is Hilbert's Hotel, a thought experiment that challenges our understanding of infinity. At first, this seems like a paradox. How can a hotel with infinite rooms be full? If the hotel has an infinite number of rooms, surely there must be one unoccupied, right? But in Hilbert's Hotel, even though every room is filled, you can still find space for new guests. The hotel's manager can simply ask every guest to move from room N to room N+1. So the guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on. In this way, room 1 becomes free, and the new guest can be accommodated. But what if an infinite number of new guests arrives? The manager can still make room by shifting each current guest to a room number that is a multiple of their current room number. For example, the guest in room 1 moves to room 2, the guest in room 2 moves to room 4, the guest in room 3 moves to room 6, and so on. This allows every new guest to occupy a new room, even though the hotel is already full. Hilbert's Hotel paradox reveals the strange properties of infinite sets. The idea that you can add new elements, guests, in this case to an infinite set without filling it up, challenges our everyday understanding of numbers and space. It shows that infinity isn't just a very large number, it behaves in ways that are completely unintuitive to our finite minds. The paradox highlights the difference between finite and infinite, showing that while the concept of infinity might seem paradoxical, it is mathematically consistent. This thought experiment invites us to rethink our assumptions about space, time, and the very nature of the infinite. It forces us to acknowledge that infinity isn't something we can fully grasp or measure in human terms, and that paradoxes arise when we try to apply finite logic to infinite concepts. Hilbert's Hotel is a mind-bending exploration of infinity that keeps us questioning the very limits of what is possible. Gabriel's Horn. Imagine a horn with an infinite length, endlessly tapering towards a point, its shape resembling the surface of a cone, but extending outward forever. This is Gabriel's horn, a thought experiment in geometry that presents a strange paradox about the relationship between surface area and volume. The horn is described by a curve that starts wide at the base and narrows toward the tip. Mathematically, it's a shape known as a frustum of a cone, with the base at a certain radius and the top shrinking as it stretches to infinity. The paradox arises when we calculate its two key properties, surface area and volume. Despite the fact that the horn extends infinitely, it has a finite volume. In fact, the total volume of Gabriel's horn is exactly p cubic units, which means that even though the horn is infinitely long, it contains a finite amount of material. Essentially, it's a finite object in terms of space. But here's where the paradox hits. The surface area of Gabriel's horn is infinite. Even though the horn occupies a finite amount of space, the surface area required to cover it would stretch out into infinity. This paradox is both mathematically fascinating and deeply counterintuitive. It challenges our everyday understanding of space, showing us that it's possible for a shape to occupy a finite amount of volume, but have an infinite surface area. We might imagine the horn as a very thin tube, getting thinner and thinner as it extends. But its infinite length means that if you tried to paint its surface, you would run out of paint before ever covering it. No matter how much paint you had, the surface of Gabriel's horn is too vast to ever be covered completely. Gabriel's horn forces us to rethink concepts we take for granted. It shows us that infinity can manifest in ways that are not immediately obvious or comprehensible. It reminds us that in the realm of the infinite, our intuitions about size and space break down. The paradox of Gabriel's horn invites us to contemplate the strange and mysterious behavior of infinite shapes and, more generally, the peculiarities of infinity itself. Infinite monkey theorem. Imagine an infinite number of monkeys typing on typewriters, each randomly pressing keys. Given enough time, according to the infinite monkey theorem, one of them would eventually type the complete works of Shakespeare, word for word, punctuation for punctuation. In fact, with infinite time, these monkeys would not only produce Shakespeare's works, but every book ever written, every song ever sung, and every poem ever composed, all mixed together in an endless, random stream of letters. The theorem is a playful yet profound exploration of randomness, probability, and the infinite. The infinite monkey theorem is often used to illustrate the idea of infinite possibilities. Mathematically, it shows that if you have an infinite amount of time, any event with a non-zero probability, no matter how unlikely, will almost certainly occur. In the case of the monkeys, the probability of typing Hamlet by chance on a single typewriter might be astronomically small, but with infinite monkeys and infinite time, the outcome is inevitable. However, the paradox here lies in how we understand randomness and the infinite. While the idea of an infinite number of monkeys might seem absurd, it highlights how extremely unlikely events can happen in an infinite or even a large finite sample. It makes us question how the infinite interacts with probability. What happens in a universe where there is endless possibility? Could randomness lead to ultimate order? Or is it simply a tangled mess? Despite its whimsical nature, the infinite monkey theorem carries deep philosophical and mathematical implications. It points to the role of probability in the infinite, showing us that under infinite conditions, randomness will always generate any possible outcome, even the most orderly and meaningful one, like the works of Shakespeare. And yet, in the infinite sea of randomness, those moments of meaning are fleeting, buried within the noise. The theorem also poses a counterintuitive thought. In an infinite universe of possibilities, everything is bound to happen eventually, but how often it happens and when it happens might still elude our comprehension, reminding us of the limits of our understanding of randomness and time. Zeno's paradox. Imagine you're running a race to a finish line that seems to be just ahead. But there's a catch. Before you can reach the finish line, you must first cover half the distance. Once you've covered that, you must cover half of what remains, then half of that, and so on, infinitely. According to Zeno's paradox, no matter how many times you halve the distance, you will never actually reach the finish line. You will always be halfway to your goal, forever approaching but never arriving. This paradox, formulated by the ancient Greek philosopher Zeno of Elea, challenges our understanding of motion, space, and time. The paradox is built on the idea of infinite divisibility. Zeno argues that because the distance can be divided into an infinite number of smaller steps, it seems logically impossible to ever complete the journey. Each step takes a finite amount of time, but there are infinitely many steps. How can you ever finish the race if there are always more steps to take? This question strikes at the heart of how we understand the continuity of space and time. The solution to Zeno's paradox lies in the concept of a limit, a foundational idea in mathematics. Though there are infinitely many steps, the sum of all the distances you cover is finite. Mathematically, the infinite series of halving distances adds up to a finite value, meaning you do reach the finish line after all. The total distance traveled is equal to the original distance, and even though you take infinitely many steps, the time it takes to complete them is also finite. Zeno's paradox serves as a profound exploration of infinity. It shows how the infinite can seem paradoxical when applied to real-world experiences, like motion. While our intuition might suggest that dividing something into an infinite number of pieces means it can never be completed, the paradox reveals that infinity behaves in ways that are both counterintuitive and mathematically coherent. In the real world, motion and time flow continuously, and what seems impossible in theory, reaching an infinite number of points, can actually happen in practice. Ultimately, Zeno's paradox invites us to reflect on the nature of reality itself. It challenges us to look beyond appearances and question how we experience the passage of time, the continuity of space, and the very idea of infinity. In the end, the race is completed not by overcoming each infinite step, but by understanding that infinity can be traversed in finite time. Thomson's lamp. Imagine a lamp with a peculiar switch. When you flip the switch, the lamp turns on, and when you flip it again, the lamp turns off. But here's the catch. The switch is flipped an infinite number of times in a finite amount of time. Each time the switch is flipped, the lamp's state alternates between on and off. The question is, what is the final state of the lamp? Is it on or off? This is the essence of Thomson's lamp, a thought experiment proposed by philosopher James F. Thomson in the 1950s. It presents a paradox about time, motion, and the continuity of events. The key idea is that the switch is flipped an infinite number of times in a finite period. Theoretically, each flip occurs after half the time of the previous flip, first after 1 second, then 1/2 second, then 1/4 second, and so on, creating an infinite sequence of actions within a limited span of time. At first glance, the situation seems impossible. How can the lamp's state be determined if the switching never actually finishes? With an infinite number of flips, it feels like the process should never conclude. So, what is the final state of the lamp? Is it on or off? Or does the paradox suggest that the lamp's state is indeterminate, unable to be settled within the framework of conventional logic? The paradox highlights a deeper problem with the concept of infinity in real-world situations. In the context of Thomson's lamp, we are forced to confront the limits of how time and actions can be divided into smaller and smaller intervals. The idea of infinite actions occurring in finite time challenges our understanding of sequence, process, and completion. We intuitively assume that an infinite sequence of actions should lead to a clear outcome. But the paradox shows that even when time is finite, the infinite can introduce ambiguity and contradiction. Thomson's lamp forces us to question the coherence of infinite processes and the limitations of our understanding of time. It invites us to think critically about how infinite actions, especially those that involve switching between states, can challenge our intuitions about the world, forcing us to grapple with the complexity of infinity and the nature of time itself. The lottery of the infinite. Imagine you're standing in front of an infinite number of lottery tickets, each with a unique number. You buy one ticket, and you're told that one of the tickets will win a grand prize. But here's the twist. The tickets are infinitely many, and you know that a single ticket will win, but you don't know which one. The paradox arises when you try to assess the probability of your ticket winning. Intuitively, with an infinite number of tickets, your chances seem to approach zero, making it feel like your ticket has no chance of winning. And yet, you are guaranteed that one ticket will win. This is the lottery of the infinite, a paradox that explores how probability and certainty interact in the context of infinity. In a typical finite lottery, your chances are determined by the ratio of winning tickets to total tickets. In an infinite lottery, however, things behave differently. Even though the number of tickets is infinite, you know that one ticket must win. But the infinite nature of the set causes a seeming contradiction. If the odds of any individual ticket winning approach zero, how can we still be certain that someone will win? The paradox forces us to confront the strange behavior of infinite sets. In classical probability theory, the chance of winning a single ticket in an infinite set would be calculated as 1 divided by infinity, which mathematically is 0. Yet the paradox shows that even though the chance for a specific ticket to win is infinitesimally small, the set itself ensures that a winner must emerge. The certainty of a winner is guaranteed by the structure of the problem, but the probability of any one ticket winning is so close to zero that it seems counterintuitive. This paradox highlights the peculiar nature of infinity in probability. It shows that when dealing with infinite sets, our normal intuition about chance and certainty can break down. It suggests that even in the realm of infinite possibilities, certainty can coexist with near-zero probabilities. The lottery of the infinite serves as a reminder that infinity is a concept that doesn't always align with our finite, everyday understanding of the world. In the face of infinity, certainty and probability can behave in ways that defy expectation, leaving us with a lingering sense of paradox. Infinity vs. eternity paradox. Imagine two concepts that seem similar but have profoundly different implications: infinity and eternity. Infinity is a concept of something that is unbounded, without end, or immeasurable. It's a mathematical idea, like the number of points on a line, or the endless division of space or time. Eternity, on the other hand, refers to an infinite amount of time, but it carries a more philosophical or temporal weight. An infinite duration, without beginning or end, stretching endlessly through past, present, and future. The infinity via eternity paradox lies in the tension between these two ideas. At first, they may seem to align perfectly. Both concepts suggest something that never ends. But when you examine them more closely, you begin to see the subtle but significant differences between the two. Infinity, when applied to space or numbers, suggests a process, a never-ending progression. It's not static. It's a potential that is always expanding or dividing further without an endpoint. For example, in mathematics, you can always add one more number to an infinite series. You can keep dividing a line into smaller and smaller segments. In this sense, infinity is dynamic, always growing but never reaching anything. Eternity, however, is a different beast. It's often considered a fixed, unchanging concept, particularly when we think of it in the context of time. Eternal time doesn't progress or divide. It simply is, existing outside the bounds of the finite experience of time. Eternity is not a process that can be divided further. It's a state of being, a timeless existence. In religious or metaphysical contexts, eternity might be the realm of the divine, the unchanging nature of the universe, or the experience of an infinite, uninterrupted present. The paradox arises when we try to reconcile these two ideas. If infinity is a never-ending process, always stretching and always divisible, then can it truly be equated to eternity, which is static and unchanging? Infinity as a process can never truly arrive at something. whereas eternity is already there, complete and whole. So while both concepts describe endlessness, they imply different things about the nature of time, change, and experience. This paradox challenges our intuitions about time, existence, and the nature of the infinite. It asks whether true infinity is a series of endless moments, always in motion, always expanding, or if eternity is a complete, unchanging state of being. Can something truly infinite ever exist in the same way something eternal does? And if time is infinite, does it ever truly become eternal? The infinity S, does it ever truly become eternal? The infinity V. Eternity paradox invites us to explore the limits of time and existence, questioning whether these two concepts can coexist or if they are fundamentally incompatible. Omega point. The omega point is a concept proposed by the French philosopher and Jesuit priest Pierre Teilhard de Chardin in the early 20th century. It refers to the ultimate state of complexity and consciousness that humanity and the universe is evolving toward. According to Teilhard, the universe is in a state of continuous evolution, both in terms of physical complexity and consciousness, and this evolution will culminate in a single point in the future, where all matter, energy, and consciousness converge into a unified, transcendent state of being. The omega point is a point of supreme complexity, harmony, and consciousness, often likened to a spiritual or cosmic end, where all life becomes connected in a greater cosmic mind. The paradox arises when you begin to consider the relationship between time, evolution, and the infinite. Teilhard de Chardin envisioned this omega point as the ultimate outcome of an evolutionary process, not just for human beings, but for the entire universe. This suggests a kind of teleology, the belief that the universe is heading toward a final, purposeful state. However, this idea creates a paradox when we try to reconcile it with other cosmological ideas, particularly the scientific understanding of the universe. On one hand, the concept of the omega point appears to suggest that there is an end point to the universe's evolutionary path, a final state where everything converges. This seems to run counter to the idea of an infinite universe that has no beginning or end. If the universe is infinite, how can it have a final point of convergence? Can there truly be a cosmic end if the universe itself is infinite and eternal? Another paradox arises when considering the nature of consciousness in this context. Teilhard's vision implies that consciousness is not just a feature of human beings, but something that will expand to encompass the entire universe, gradually becoming more complex and unified. But how can consciousness reach such a state of absolute unity without contradicting our current understanding of individual autonomy and free will? Would this omega point require a collective merging of all consciousness, or would each individual remain unique in the face of such transcendence? Moreover, the idea of the omega point also brings up the issue of time and eternity. If the universe is evolving toward this ultimate state, does that imply an eventual end to time itself? What would happen to the flow of time when the universe reaches the omega point, where everything converges and is eternally connected? The omega point paradox forces us to confront profound questions about the future of the universe, the nature of evolution, and the relationship between time, consciousness, and infinity. It challenges our perceptions of how the cosmos operates, suggesting that it might not be an endless, random process, but one with a final purpose and outcome. Whether or not this vision is scientifically valid, the idea of the omega point continues to inspire deep philosophical and theological debates about the fate of the universe and the ultimate potential of humanity. Problem of induction. Imagine you're standing outside on a clear morning, watching the sun rise in the east. Every day for your entire life, the sun has risen in the east. From this, you confidently predict that tomorrow the sun will also rise in the east. This seems perfectly reasonable, even obvious. But this is exactly where the problem of induction comes into play, a paradox that challenges the very basis of how we predict future events based on past experiences. The problem of induction, famously articulated by philosopher David Hume in the 18th century, asks, Why should we believe that the future will resemble the past? In this case, just because the sun has risen in the east every day up until now, does that logically guarantee it will rise in the east tomorrow? Hume argued that we have no rational justification for assuming that patterns we observe will continue indefinitely. Our belief in the regularity of nature is based on habit and experience, not logical proof. Inductive reasoning, the process of making generalizations based on specific observations, is central to how we navigate the world. We infer that certain patterns will continue because they have always done so. But Hume's problem forces us to recognize that no matter how many times we observe the sun rising in the east, each individual observation is a separate event. The fact that the sun has risen in the east for thousands of years doesn't logically prove it will do so tomorrow, because the future isn't guaranteed by past events. Each new sunrise is an untested event that could break the pattern. The problem of induction raises a deeper philosophical issue about knowledge itself. If our understanding of the world is based on inductive reasoning, can we ever have certainty about anything? How do we justify our belief that patterns in nature will continue? If we can't prove that the future will resemble the past, what does that say about our confidence in science, predictions, or even basic expectations in daily life? Philosophers have offered various responses to the problem of induction. Some suggest that induction is simply a pragmatic necessity, that it works for all practical purposes, even if it lacks a logical foundation. Others, like Karl Popper, argued that scientific knowledge progresses not by induction, but through falsification, by testing hypotheses and disproving them, rather than assuming they will always be true. In the end, the problem of induction reminds us that even our most basic expectations about the world are built on fragile foundations. It forces us to confront the limits of human reasoning and to consider that while the future may often resemble the past, we cannot be certain that it always will. Paradox of the simulation argument. Imagine that we live in a highly advanced simulation created by a future civilization with immense computing power. The simulation is so detailed that every aspect of our world, every moment of our lives, is programmed and played out within a virtual reality indistinguishable from true reality. Now, consider the simulation argument proposed by philosopher Nick Bostrom. He argues that one of three possibilities must be true. Humanity will go extinct before reaching a level of technological maturity capable of creating realistic simulations of reality. Highly advanced civilizations will not be interested in running simulations of their ancestors. We are almost certainly living in a simulation, because if advanced civilizations do run simulations, they would run many, and the number of simulated realities would vastly outnumber the single original reality. The paradox lies in the unsettling implications of this argument. If we are indeed living in a simulation, we might never know. All of our experiences, everything we perceive, everything we think is real, could be artificially created by some external intelligence. What does it mean for our understanding of existence if this reality is just a sophisticated program running in the background of some cosmic computer? The paradox becomes even more troubling when we consider the probability of being in a simulation. If future civilizations are capable of creating highly detailed simulations, they would likely create many of them, vastly outnumbering the base or original reality. This means that statistically, the chances of us being in a simulated reality are much higher than the chances of us living in the real one. This paradox challenges everything we take for granted about the nature of reality. If our world is a simulation, how can we ever truly know? Can we trust our senses, our memories, or even our most basic beliefs about existence? The simulation argument forces us to confront the possibility that everything we know and feel might be nothing more than a well-crafted illusion, leaving us to wonder whether reality, as we understand it, is ever truly real. Schrödinger's cat. Imagine a cat inside a sealed box, along with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The setup is based on a thought experiment by physicist Erwin Schrödinger, The radioactive atom has a 50% chance of decaying in 1 hour, and if it does, the Geiger counter will trigger the hammer to break the vial of poison, killing the cat. If the atom does not decay, the cat will remain alive according to the principles of quantum mechanics. Until we open the box and observe the situation, the atom exists in a superposition, both decayed and not decayed, and as a result, the cat is simultaneously both alive and dead. The act of observation forces the system to choose a state, either alive or dead. This is the Schrödinger's cat paradox, a way of illustrating the strange nature of quantum mechanics, where particles can exist in multiple states at once, only collapsing into a definite state when measured or observed. The paradox is mind-boggling. How can the cat be both alive and dead? In our everyday experience, an object is either one thing or another, but at the quantum level, things don't behave that way. A particle, such as the radioactive atom, can exist in multiple possible states at once, a concept known as superposition. It is only when an observer interacts with the system, forcing it into a definite state, that the quantum superposition collapses into one outcome. In Schrödinger's scenario, the cat's fate mirrors this strange behavior, where until observed, it exists in both states simultaneously. This paradox reveals the profound difference between classical physics, which deals with definite outcomes, and quantum mechanics, where uncertainty and duality are fundamental. It challenges our basic intuitions about reality, suggesting that the act of observation itself plays a crucial role in determining the state of the world. Schrödinger's cat paradox forces us to question the nature of reality itself. Is the world inherently indeterminate, only gaining certainty once we observe it? Wigner's friend. Imagine a scientist, Wigner, conducting an experiment in a laboratory where a quantum measurement is being performed on a particle. According to quantum mechanics, the particle can exist in a superposition of states until it is observed, at which point the wave function collapses into a definite outcome. Now, Wigner's friend is inside the laboratory, conducting the experiment, and, according to quantum mechanics, the friend's observation also causes the collapse of the wave function, forcing the particle to assume a definite state. But here's the twist. Wigner, who is outside the lab, doesn't know the result of the experiment. From his perspective, the wave function of the system, which includes both the particle and his friend, is still in a superposition. Wigner cannot say that the experiment's outcome is definite until he observes the result himself. This scenario, known as Wigner's friend, presents a deep paradox in quantum mechanics. It illustrates the clash between the subjective experience of an observer and the objective reality predicted by quantum theory. The paradox arises because Wigner believes that, until he observes the system, everything is still in superposition. However, his friend inside the lab, who has made the observation, would claim the wave function has collapsed and the result is definite. The question is, which perspective is correct? Is it Wigner's, who sees the system as still in superposition, or is it the friend's, who sees a definite state? This paradox raises fundamental questions about the nature of observation and reality in quantum mechanics. Does the state of a system depend on the observer, or is there an objective reality that exists regardless of who is observing? Wigner's friend challenges our understanding of what constitutes an observer in quantum theory, and whether consciousness plays a role in determining the outcome of a quantum event. It forces us to confront the strange and counterintuitive implications of quantum mechanics on our perception of reality. Delayed choice experiment. Imagine you're setting up a simple experiment with light, using a beam splitter to direct it down two paths, both leading to detectors. Normally, in classical physics, once the light takes one path, it behaves like a particle, while if it travels both paths simultaneously, it behaves like a wave. But now, consider the delayed choice experiment, a thought experiment proposed by physicist John Wheeler. The twist is that you don't decide whether to measure the particle-like or wave-like behavior until after the light has already passed through the beam splitter. Even more mind-boggling, The light doesn't know that you're making the choice until after it has traveled down its path, suggesting that the decision to treat it as a wave or a particle depends on whether you measure it in one way or the other. In the delayed choice scenario, you could set up the experiment so that, after the light passes through the splitter, you wait until the light has reached the detectors to decide whether to use equipment that will measure it as a particle or a wave. The light's behavior, whether it acts like a particle with a definite path or like a wave with interference patterns, seems to depend on the measurement you make after the light has already passed through the beam split. This suggests that the future measurement choice influences the past behavior of the light. The paradox challenges our traditional understanding of time and causality. How can a decision made in the present affect how light behaved in the past? The delayed choice experiment forces us to confront the strange nature of quantum mechanics, where the act of measurement doesn't just reveal information, it seems to determine the outcome. It blurs the line between past, present, and future, and raises the question of whether reality itself depends on our choices or actions, as if the universe is waiting for us to decide how to interpret it. Quantum Zeno effect. Imagine a particle that is decaying over time, a process that normally happens randomly. In quantum mechanics, particles like atoms or subatomic particles have a certain probability of decaying at any given moment. Now, suppose you try to observe this particle frequently, so often that you catch it in the act of decaying repeatedly before it has a chance to fully decay. Strangely, the particle seems to avoid decaying. The more often you measure it, the less likely it is to undergo the decay. This is the quantum Zeno effect, a paradoxical phenomenon in quantum mechanics where frequent observation can prevent a system from evolving, effectively freezing it in its current state. The quantum Zeno effect is named after the ancient Greek philosopher Zeno, who proposed paradoxes about motion and change. In quantum mechanics, the effect reveals that continuous measurement of a quantum system can interfere with its natural evolution. It's as if by observing the system you are halting its natural process. The more you observe, the less the system has the opportunity to change. This effect is rooted in the peculiarities of quantum mechanics, where particles exist in superposition and their state isn't fully determined until they are measured. This paradox challenges our everyday understanding of observation. We tend to think that measuring something reveals its state without fundamentally altering it. However, in quantum mechanics, the act of measurement isn't just a passive observation, it can actively influence the behavior of the system. The quantum Zeno effect suggests that, in the quantum world, time and change don't always proceed in predictable ways. It's as if the very act of watching prevents the natural course of events from unfolding, forcing us to reconsider the relationship between the observer and the observed. The quantum Zeno effect provides a fascinating glimpse into the strange and counterintuitive nature of quantum mechanics, where the line between observation and reality blurs, leaving us with more questions than answers about the true nature of time and existence. Quantum suicide and immortality. Imagine a thought experiment in which a person is placed in a situation where they repeatedly face life or death decisions, but with a quantum twist. In the quantum suicide thought experiment, the individual is placed in front of a quantum mechanism that triggers a lethal event based on the outcome of a quantum measurement, such as the spin of a particle. The person's life depends on the quantum state being in a particular configuration. Let's say if the particle is measured to spin a certain way, the individual dies, but if it spins the other way, they survive. The paradox lies in the interpretation of quantum mechanics and the many worlds hypothesis. According to this theory, every possible outcome of a quantum measurement happens in some branch of the universe. If the person survives the quantum event in one branch of the universe, they are consciously aware of their survival. But in other branches, where the quantum measurement leads to their death, their consciousness would no longer continue. From the perspective of the person, they would never experience their own death because they would always find themselves in a branch where they survive. This leads to the strange conclusion that, in a sense, the person is immortal in their own experience, surviving an infinite number of quantum suicides. Each time, their consciousness persists in the universe where they continue to live, while all other versions of themselves perish. The quantum suicide and immortality paradox raises unsettling questions about the nature of consciousness and the multiverse. If we accept the many worlds interpretation of quantum mechanics, could this form of subjective immortality actually be possible? And if consciousness can persist in one branch of the multiverse, does that imply that the experience of life is not bound to a singular reality, but instead exists across countless possibilities? This thought experiment challenges our understanding of life, death, and the quantum universe, leaving us to ponder whether immortality could exist in a reality where every possibility unfolds simultaneously. Many worlds paradox. Imagine a world where every decision you make, every action you take, splits reality into multiple, branching timelines. Each possible outcome of every decision you face creates a new universe where that particular outcome is realized. This is the essence of the many worlds paradox, which arises from the many worlds interpretation, MWI, of quantum mechanics. According to MWI, every quantum event, such as the flipping of a coin or the decay of an atom, does not collapse into a single outcome, but instead creates a branching universe for every possible result. This leads to an infinite number of parallel universes, each one slightly different from the other, existing simultaneously. The paradox comes into play when you consider the consequences of such an interpretation. If every choice creates a new reality, it implies that an infinite number of versions of you exist across an infinite number of universes. In one universe, you might have chosen to become a doctor, in another, an artist, and in yet another, you might have taken a different route to work. But if all these versions of you exist, how do you truly understand the real you? Are you just one iteration among countless others? And if so, does that diminish the significance of your choices? The many worlds paradox challenges our understanding of existence itself. It suggests that every time you make a decision, a new version of reality is created. But if this is true, what does it mean to live in a singular reality? Are we constantly slipping between different worlds? And if so, do we ever really know which one is real? This paradox forces us to reconsider the very nature of identity, free will, and the universe itself. It raises profound questions about how we experience reality and whether our individual choices are truly unique or just one among infinite possibilities. Observer effect. Imagine you're standing by a pond, watching a leaf float on the surface. You know that the leaf is moving because of the wind, but the moment you observe it closely, you might notice small ripples or changes in the water that were previously unnoticed. The very act of your observation changes the way the leaf moves, affecting its path. This is the essence of the observer effect, a concept that appears in both physics and psychology, but takes on its most profound form in quantum mechanics. In quantum mechanics, the observer effect refers to the idea that the act of measurement or observation can alter the state of a quantum system. This is famously illustrated in the double-slit experiment, where particles such as electrons behave as both waves and particles, depending on whether they are observed. When unobserved, they pass through both slits simultaneously, creating an interference pattern. But as soon as they are measured, observed, they behave like particles and create a different, more predictable pattern. The wave function, which represents all possible states of the system, collapses upon observation, and the particles take a definite form. The observer effect challenges our intuition. In the classical world, observation doesn't seem to change what we observe. If you watch a car drive by, its motion isn't affected by your attention to it. But in the quantum realm, the mere act of observation seems to influence the very behavior of particles, suggesting that reality is not fixed until it is measured. This raises profound philosophical questions about the nature of reality. Is the universe truly objective, or does it depend on the presence of an observer to define its state? Does the act of observation create reality itself? The observer effect forces us to confront the strange relationship between consciousness, measurement, and the physical world. It suggests that in the quantum world, reality is inherently tied to our ability to observe and measure it, and that the very act of looking might be the thing that shapes the universe around us. Heisenberg's uncertainty principle. Imagine you're trying to measure both the position and velocity of a tiny particle, like an electron. You focus all your energy on pinpointing its position as accurately as possible, but as you do, the measurement of its velocity becomes increasingly uncertain. On the other hand, if you focus on measuring its velocity precisely, the position becomes less clear. This is the essence of Heisenberg's uncertainty principle, a fundamental concept in quantum mechanics that states that you cannot simultaneously know both the exact position and the exact momentum, which includes velocity, of a particle with absolute certainty. The more precisely one of these properties is measured, the less precisely the other can be known. This principle isn't a limitation of our measuring instruments, but rather a fundamental property of nature itself. It arises from the wave-particle duality of quantum objects. In quantum mechanics, particles are described by wave functions, and the position and momentum are related by a mathematical equation. When you try to measure one property with extreme precision, the wave function spreads out, introducing uncertainty in the complementary property. This inherent uncertainty is not due to technological limitations, it's a feature of the quantum world. Heisenberg's uncertainty principle upends our classical intuitions. In the everyday world, we can measure the position and velocity of objects with great accuracy. At the same time, think of tracking a car's speed and location. But in the quantum realm, uncertainty is a built-in feature of reality. It forces us to accept that, on a fundamental level, the universe does not allow us to have complete knowledge of a particle's behavior. Instead, we can only describe the probabilities of its position and momentum, not their exact values. This paradox is deeply philosophical. It suggests that at the smallest scales, nature itself is inherently unpredictable. It raises questions about determinism and free will in the quantum realm, forcing us to reconsider how we think about knowledge, measurement, and the very nature of reality. Heisenberg's uncertainty principle reminds us that the universe on a quantum level is not as neatly ordered and predictable as we might have hoped. Instead, it is governed by a deep and unavoidable uncertainty. Wheeler's participatory universe. Imagine a universe where reality doesn't fully exist until we observe it. According to John Archibald Wheeler's participatory universe, the act of observation is not just a passive process, but a fundamental part of creating reality itself. Wheeler, one of the most influential physicists of the 20th century, proposed that the observer plays an active role in shaping the universe at the quantum level. This is a radical departure from traditional physics, where the universe is thought to exist independently of our observation. In Wheeler's view, the act of measurement, or participation, by conscious beings is essential to the unfolding of reality. Wheeler's idea stems from the strange behavior of particles in quantum mechanics. In experiments like the double-slit experiment, particles like electrons exist in multiple states simultaneously, superposition, until observed, at which point they collapse into a single, definite state. Wheeler extended this idea, suggesting that not only does observation affect particles at the quantum level, but that the entire universe may depend on conscious participation. In this view, the universe doesn't have a fixed, objective reality until it is measured or observed. It's as if the cosmos needs an observer to bring it into existence at every moment. Wheeler famously coined the term "it from bit," meaning that all physical reality could be derived from information. He proposed that the most fundamental building blocks of the universe might not be particles or fields, but rather bits of information, which only become meaningful through interaction and observation. In this framework, consciousness doesn't just passively record what happens in the universe, it actively participates in creating the very fabric of reality. The participatory universe paradox challenges our intuitions about reality. If the universe depends on our observation to take shape, does it mean that we are, in a way, co-creators of the cosmos? And if our observations shape reality, how much control do we really have over what we experience? Wheeler's theory raises profound questions about the relationship between the observer and the observed, and about the very nature of existence itself. It invites us to reconsider not only how we perceive the universe, but how we might be an intrinsic part of its continuous unfolding. Holographic principle. Imagine that everything you perceive as three-dimensional reality, the world around you, the objects you interact with, even yourself, is actually a projection of information stored on a distant two-dimensional surface. This is the essence of the holographic principle, a theoretical idea in physics that suggests the entire universe can be described by information encoded on a two-dimensional boundary, much like how a hologram encodes three-dimensional images on a flat surface. The idea emerges from the study of black holes and the behavior of information near them. According to the Bekenstein-Hawking entropy formula, black holes have a finite amount of information encoded on their event horizons, the boundary beyond which nothing, not even light, can escape. This information is proportional to the surface area of the black hole, not its volume. This observation led physicists like Gerard T. Hooft and Leonard Susskind to propose that the information content of a region of space might be encoded not in the volume, as we typically assume, but on a 2D surface surrounding it. In simpler terms, the holographic principle suggests that the inside of a black hole, or perhaps even our entire universe, could be described by a set of data points on a flat two-dimensional surface. This idea is analogous to how a hologram works. The full three-dimensional image is encoded in a two-dimensional surface, and when light shines on it in just the right way, a 3D image is projected. The paradox of the holographic principle lies in how it challenges our basic understanding of space and reality. If our universe is a hologram, it implies that all the three-dimensional experiences we have are simply projections of data stored on a distant, possibly cosmic boundary. This raises profound questions. How do we reconcile this two-dimensional foundation with our experiences of depth, volume, and physicality? Are we simply living in a vast projection, like a cosmic illusion? And if the universe can be described in two dimensions, what does that say about the nature of reality itself? The holographic principle opens a doorway to deep and unresolved questions about the nature of space, time, and information. It challenges us to rethink not only the structure of the universe, but the very way we understand reality. It suggests that perhaps the real world is not the one we experience, but something encoded and projected from a deeper, more fundamental surface beyond our comprehension. Laplace's demon. Imagine a vast, all-knowing intellect, let's call it Laplace's demon, that has complete knowledge of the current state of every particle in the universe. This being knows the exact position and momentum of every atom, every star, every molecule, and even the smallest grain of dust, as well as the laws of physics governing their interactions. Given this perfect knowledge of the present, Laplace's demon could calculate with absolute certainty the past and future of the entire universe. Every event, every action, and every decision would unfold in a deterministic manner, following from the initial conditions of the universe. In this view, the future is entirely predictable, and free will becomes an illusion, because every action is the inevitable result of prior causes. Laplace's demon is based on a deterministic worldview, where the future is set by the present and the past, and there are no random elements. If we knew the positions and velocities of all particles, we could predict the universe's future with perfect accuracy. This idea aligns with classical mechanics, where the laws of motion, as formulated by Isaac Newton, govern the behavior of objects. In this framework, the universe is like a giant machine, running in a straight line from the past into the future, with no room for chance or indeterminacy. However, this deterministic view runs into problems with the advent of quantum mechanics. Quantum theory introduces randomness and uncertainty at the subatomic level, famously illustrated by Heisenberg's uncertainty principle. According to quantum mechanics, even with perfect knowledge of a particle's position, its momentum can never be fully known. This unpredictability challenges the concept of Laplace's demon, suggesting that the universe may not be as deterministic as once thought. The Laplace's demon paradox raises deep questions about determinism, free will, and the nature of reality. If the future is truly determined, then what role do we play in shaping our lives? Is free will an illusion? Or is there more to reality than the predictable chain of causes and effects? The paradox forces us to confront our beliefs about the universe and the fundamental laws that govern it. Boltzmann brain. Imagine you're living in a vast, infinite universe where time and space extend endlessly. The universe, governed by the laws of thermodynamics, naturally tends toward disorder over time. This is the backdrop for the Boltzmann brain paradox, a disturbing thought experiment that arises from the implications of statistical mechanics in an infinite universe. According to the laws of probability, in an infinite universe, random fluctuations can lead to the spontaneous formation of complex structures, including conscious beings. The paradox suggests that, given infinite time, it's statistically more likely for a single brain, complete with false memories, perceptions, and experiences, to spontaneously form out of pure chaos, rather than for a stable, lasting universe like the one we experience. This so-called Boltzmann brain would emerge purely from random particles assembling in just the right configuration, creating a temporary, self-aware entity. This brain would have no connection to a larger, stable environment, but it would experience a brief flash of consciousness, possibly with memories, that make it feel like it has lived a normal life. The problem with this scenario is that in an infinite universe, these random, isolated brains could outnumber actual, stable observers like ourselves. This leads to a strange and unsettling question. If we are just random fluctuations in an infinite universe, how can we be sure we are not Boltzmann brains, having false memories of a real world? The Boltzmann brain paradox challenges our understanding of reality. It questions the reliability of our perceptions, the nature of existence, and the validity of our memories. If the odds of spontaneously generating a conscious brain are so high in an infinite universe, then it seems more likely for a brain to form in isolation than for a stable, orderly universe like the one we live in to persist. This paradox forces us to rethink what it means to be real, and whether our entire experience might be a fleeting, random occurrence rather than a stable, meaningful existence. Fermi paradox. Imagine you're staring into the vast, star-filled sky, contemplating the universe's vastness and the billions of potentially habitable planets that must exist. Given the enormity of the cosmos, it seems almost certain that intelligent extraterrestrial life must be out there. And yet, despite the countless stars, galaxies, and planets, we have found no definitive evidence of alien civilization. This is the Fermi paradox, the puzzling contradiction between the high probability of extraterrestrial life and the complete lack of evidence or contact with such civilization. The paradox is named after physicist Enrico Fermi, who famously remarked, "Where is everybody?" in the 1950s, after discussing the vast number of potentially habitable planets in our galaxy. With millions of stars similar to the Sun, many of which likely have planets in the habitable zone, the odds seem overwhelmingly high that other intelligent life forms have developed. And yet, despite decades of searching, including efforts like SETI, Search for Extraterrestrial Intelligence, we have found no signals, no communications, no visits. It raises the question, if the universe is so large and the conditions for life are so common, why haven't we encountered any signs of alien life? Several hypotheses attempt to explain this paradox. One possibility is that advanced civilizations may be exceedingly rare, or that they self-destruct before they can communicate across the vast distances of space. Another idea is that extraterrestrial civilizations may deliberately avoid us, either out of fear or because they consider us unworthy of contact. It's also possible that alien life exists, but it is so different from our understanding that we are unable to detect it. The Fermi paradox forces us to reconsider our place in the cosmos. If we are alone, why is that? Or if we are not, What is preventing us from finding the evidence of others? This paradox leaves us with profound questions about the nature of life, intelligence, and our place in the universe. Doomsday argument. Imagine standing in a room with a group of people, and you're told that at least one of you will die in the next year. The question is, how likely are you to be the one to die? Intuitively, you might think the odds are equal for everyone, but the doomsday argument introduces a thought-provoking twist. This argument, which applies to the entire human race rather than a single person, uses probability to suggest that the chances of humanity going extinct in the near future might be higher than we think, based on our place in the timeline of human history. The doomsday argument is grounded in the concept of self-sampling assumption, which suggests that you can estimate the likelihood of an event by considering your position in a larger group. If you randomly find yourself in the middle of a sequence, it's reasonable to assume that you are likely near the average. Applying this logic to humanity, the argument posits that because we are alive in the early stages of the history of human civilization, a relatively small fraction of human existence, the probability that the human race is nearing its end is greater than we tend to assume. If humanity were near the end of its timeline, we would expect to be in the early stages, given our random position in this hypothetical sequence of human existence. The paradox is that while this reasoning leads to the conclusion that we are at a higher risk of extinction than we might think, it challenges our optimistic assumption that humanity has a long and secure future ahead. The doomsday argument forces us to confront the unsettling possibility that we might be living in the early years of humanity's existence, and that the end could be much nearer than we anticipate. It raises profound questions about the future of humanity and the nature of probability in shaping our existential risks. Problem of evil. Imagine a world where immense suffering and evil exist. Natural disasters, illness, and human cruelty are widespread. You look up to the heavens and ask, if there is an all-powerful, all-knowing, and benevolent God, why does such evil persist? This is the core of the problem of evil, one of the oldest and most profound challenges in philosophy and theology. The problem centers on the apparent contradiction between the existence of a perfect deity and the reality of suffering in the world. If God is all-powerful and all-good, then why does evil exist? One common response is the free will defense, which argues that God gave humans free will, and the existence of evil is a consequence of humans misusing this freedom. In this view, evil is a necessary condition for true moral agency, where humans are free to choose between good and evil. However, this doesn't explain why natural evils, such as earthquakes, diseases, and other disasters, exist. These events cause immense suffering, but are not the result of human choice. If God is all-knowing, why allow these random acts of suffering? Another response is that evil and suffering are part of a larger divine plan that humans cannot fully comprehend. Perhaps suffering serves a greater purpose, such as allowing for growth, character development, or spiritual enlightenment. But this raises another question. Why must so much suffering occur in such extreme forms? Why is it that some innocent people experience such unbearable hardship while others live in relative ease? The problem of evil forces us to confront deep questions about the nature of God, the universe, and human existence. It challenges the assumptions about divine justice and invites reflection on how we reconcile the existence of evil with the concept of a benevolent, all-powerful deity. The paradox remains one of the most enduring and perplexing dilemmas in the philosophy of religion, asking whether the presence of evil fundamentally undermines the idea of a perfect God. Pascal's wager. Imagine you're faced with a decision, whether to believe in God. The stakes are incredibly high and the evidence is unclear, so you wonder, what should you do? Blaise Pascal, a 17th century philosopher, proposed a solution to this dilemma known as Pascal's wager. The wager is not a proof of God's existence, but rather a pragmatic argument for belief. Pascal suggested that, in the face of uncertainty, the safest bet is to believe in God. Here's how it works. If you choose to believe in God and God exists, you gain eternal happiness in heaven. If God doesn't exist, you lose very little, perhaps some earthly pleasures. On the other hand, if you choose not to believe and God exists, you face eternal punishment in hell, which is the worst possible outcome. But if you don't believe and God doesn't exist, there's no consequence. Therefore, the potential gain of believing in God, eternal happiness, far outweighs the potential loss, a limited earthly sacrifice, while the potential loss of not believing, eternal damnation, is infinitely worse than the potential gain of living a life without belief. Pascal's wager presents a kind of risk management approach to faith, suggesting that even without concrete evidence of God's existence, the rational choice is to believe. The wager turns belief into a calculated decision based on the extreme consequences of the possible outcomes. It appeals to reason rather than religious experience, urging that the fear of eternal loss makes belief a safer bet than atheism. However, the paradox lies in the simplicity of the wager. It assumes that belief in God is a choice, something you can decide to do for pragmatic reasons. It also raises questions about the nature of true belief. Can belief be genuine if it's based solely on a calculated risk? Pascal's wager forces us to consider faith as a rational decision, but also challenges the authenticity of belief when it's motivated by self-interest rather than conviction. Moral luck paradox. Imagine two drivers, both speeding down a highway. One driver, let's call him driver A, swerves to avoid a pedestrian and, in doing so, accidentally crashes into another car. Driver A is severely injured, but the pedestrian survives unharmed. Now consider driver B. They're speeding too, but unlike driver A, they don't swerve in time, hitting the pedestrian and causing fatal harm. The difference in the outcomes of their actions seems to hinge purely on luck. Driver A's accident resulted in harm to themselves but no one else, while driver B's actions led to a tragic death. This is the moral luck paradox, which raises questions about how much of our moral judgment should depend on factors beyond our control. Moral luck is the idea that individuals can be judged morally for actions or outcomes that are influenced by factors outside their control. In the case of the two drivers, both made the same decision to speed, but the outcomes were drastically different due to sheer luck. Driver A's good luck resulted in no harm to others, while driver B's bad luck led to the death of a pedestrian. If both drivers had the same intentions and performed the same actions, should we really judge them so differently based on their luck? The paradox challenges our intuition about moral responsibility. In traditional ethics, we often assume that individuals are morally responsible for their actions based on their intentions or the choices they make. But moral luck complicates this, showing that outcomes can drastically change based on factors beyond the agent's control. If driver A and driver B are judged differently for actions they essentially had no control over, what does that say about the fairness and consistency of moral judgment? The moral luck paradox forces us to reconsider how we assign moral responsibility. If luck can affect our moral standing, can we truly hold people accountable for outcomes that are, in part, out of their hands? It raises deep questions about justice, fairness, and the role of luck in shaping our ethical lives. Experience machine. Imagine a machine that could perfectly simulate any experience you desire. Plug into it and you could live out your wildest fantasies free from pain, suffering, or disappointment. Every moment would be blissful. Every sensation precisely tailored to your liking. In this world, you would be able to enjoy a life of ultimate happiness without any of the challenges or struggles of reality. But here's the catch. Once you enter the machine, you would never know you were inside it. Everything would feel real, but in fact, you would be living in a simulated world, detached from actual experiences and reality. This is the essence of the experience machine, a thought experiment proposed by philosopher Robert Nozick to challenge the value of real experiences versus simulated pleasure. The paradox comes into play when we consider the question, would you plug into the experience machine? Nozick's experiment raises a profound ethical dilemma. On one hand, the machine offers you eternal pleasure, satisfaction, and the avoidance of pain. But on the other hand, you would no longer experience life authentically. Your relationships, achievements, and emotions would be fabricated by the machine, leaving you trapped in a world that feels real but lacks any true substance. Nozick's argument suggests that most people would choose not to enter the machine, implying that there's more to life than mere pleasure. We value real experiences, genuine relationships, and the sense of autonomy that comes with living a life full of challenges and growth. The experience machine paradox forces us to reflect on the nature of happiness and fulfillment. Is the pursuit of pleasure alone enough to lead a meaningful life? Or is there something deeper and more significant that comes from facing reality with all its ups and downs, rather than seeking a perfect, painless existence in a simulated world? The thought experiment invites us to question what we truly value in life, and whether pleasure can ever substitute for a life lived authentically. God paradox. Imagine a being so powerful, so perfect, that it is beyond comprehension. A being who can do anything, even things that seem logically impossible. This is the essence of the God paradox, a philosophical dilemma that questions the nature of omnipotence. If God is omnipotent, can God create a rock so heavy that even He cannot lift it? On the surface, this seems like a straightforward paradox. If God can do anything, then surely He should be able to do this. But if God cannot do something as simple as lifting a rock, then doesn't that limit His power? This leads to a deeper question. Does omnipotence include the ability to perform logically contradictory tasks, or is it limited by the constraints of logic itself? The God paradox highlights a conflict between the concept of unlimited power and the nature of logical consistency. If we say that God is all-powerful, do we mean He can do anything, including things that defy logic? Or do we mean that His power is confined to that which is logically possible? If omnipotence includes the ability to perform logical contradictions, then it would imply that the very idea of omnipotence could become meaningless. For example, could an omnipotent being create a square circle? This is an inherent contradiction, as a square and a circle are, by definition, mutually exclusive. On the other hand, if God's power is constrained by logic, it seems that even omnipotence has limits. But then, does this reduce God's omnipotence? Or is it simply that logic is a necessary foundation for any coherent existence, even for an all-powerful being? The God paradox doesn't offer a definitive answer. It forces us to confront the limits of language, logic, and our understanding of power. It asks whether omnipotence, in its true sense, is possible, or if even infinite power must be subject to the rules of reason. Paradox of nihilism. Imagine a person who believes that life is ultimately meaningless. There is no inherent purpose, no objective morality, and no lasting significance to our actions. This person subscribes to nihilism, the philosophical view that rejects the existence of any intrinsic meaning in the universe. On the surface, this seems like a liberating belief, free from the constraints of external purpose. However, this belief leads to a paradox. If life is truly meaningless, and all values, goals, and purposes are subjective or illusory, then how can a nihilist find the motivation to act, pursue goals, or even maintain any form of personal integrity? If nothing has inherent value, why do anything at all? The paradox of nihilism arises from the tension between rejecting meaning and still living within a world that appears to function with purpose and value. While nihilism might suggest that life's meaning is a human construction, dependent on perception and subjective experience, it doesn't necessarily provide a clear guide on how to navigate this lack of meaning. Nihilists often reject conventional frameworks like religion, morality, or societal goals, but without these structures, they face the dilemma of how to construct a meaningful life at all. This can lead to a sense of emptiness, as even personal desires or motivations become subject to the same nihilistic view, that life itself is without inherent worth. However, some nihilists argue that recognizing the absence of inherent meaning is, in itself, a form of liberation. By accepting that life has no objective purpose, individuals can create their own values and live authentically according to their desires, unburdened by societal expectations. The paradox of nihilism thus challenges us to think about how we define meaning and purpose in our own lives, even when confronted with the possibility that these may ultimately be illusion. It forces us to consider whether meaning is something we must find, create, or simply embrace as a fleeting experience in an indifferent universe. Paradox of being. Imagine you exist. You are aware of yourself, your thoughts, your experiences, and your surroundings. But what does it mean to be? The paradox of being arises when you try to define the essence of your own existence. On one hand, you know that you exist because you can think, feel, and perceive the world around you. This is Descartes' famous declaration, cogito ergo sum, I think, therefore I am. It seems simple and undeniable, but when you attempt to understand why or how you exist, things become more complex. The very act of asking, why do I exist, or what is the purpose of my being, forces us into a circular logic. To ask these questions, you must already exist to ask them. This paradox challenges our understanding of existence itself. It is one thing to acknowledge that you exist, but quite another to comprehend why you exist, or to grasp the nature of existence itself. If you are existing in the present moment, how can you ever be sure of your essence when everything you experience is transient? Every moment that passes, you are changing. The person you were a second ago is not exactly the person you are now, and yet there is a continuity of being, a sense of self that persists across time. But what is the true nature of this self? If everything is constantly changing, can it be said that any aspect of your being truly exists in an unchanging, stable sense? The paradox of being asks us to confront the limits of self-awareness. To know you exist is one thing, but to understand how or why is an infinite, complex journey that may never fully be resolved. It forces us to reconsider the very nature of existence and challenges our assumptions about continuity, identity, and the nature of reality itself. Paradox of consciousness. Imagine you're fully aware of your surroundings, the sights, sounds, and sensations that make up your experience of the world. You can think about your thoughts, reflect on your emotions, and even contemplate your own existence. But here lies the paradox of consciousness. Despite being acutely aware of your experience, you cannot directly access or explain the nature of that awareness. You experience consciousness, but you can never fully grasp or describe how it comes to be or how it works. At its core, the paradox asks, how can we be aware of something, yet unable to explain it? We can describe our experiences and make sense of the world around us, but when it comes to the mind itself, we face profound difficulties. What is the nature of subjective experience? The feeling of being you and having a first-person perspective. While science can explain the mechanics of the brain, neurons firing, electrical impulses, and chemical processes, this doesn't explain the subjective experience itself, the qualia of what it feels like to be conscious. How does the brain, a physical object, give rise to the immaterial sensation of awareness? The paradox becomes even more challenging when you consider that consciousness seems to arise from unconscious processes. We are unaware of most of the brain's activities, yet those activities produce the conscious experiences that define our reality. So, how does something as intangible as consciousness emerge from something as physical as the brain? The paradox of consciousness leads us to question the very foundation of reality. Are we more than just the sum of our parts? Is consciousness a product of physical processes, or is it something irreducible, something that cannot be fully explained by science? This paradox forces us to confront the limits of human understanding. leaving us to wonder whether consciousness is a mystery that will always elude explanation, or if one day we might unlock the secret of what it truly means to be aware. Simulation paradox. Imagine that our entire reality, the world, the universe, and everything in it, is a highly advanced simulation created by a far more technologically sophisticated civilization. In this scenario, everything you experience, from your thoughts to the stars above, is just a set of programmed data points, a constructed illusion. The simulation paradox arises when you consider the implications of this idea. If we are living in a simulation, how can we ever know? And if the simulation is perfect, indistinguishable from reality, can we ever truly escape it, or even prove that we are within one? The paradox deepens when we consider the possibility of an advanced civilization creating countless simulations of reality. If such simulations are possible, the number of simulated realities would vastly outnumber the one real universe. According to philosopher Nick Bostrom's simulation argument, at least one of three possibilities must be true. Either civilizations never reached the technological capability to create realistic simulations, advanced civilizations lose interest in running simulations, or we are likely living in a simulation ourselves. If the third possibility is true, then statistically, the odds of being in the base reality, the original universe, are incredibly low, and the likelihood of living in a simulation increases dramatically. The simulation paradox challenges our fundamental beliefs about reality and existence. If we are in a simulation, does that mean our perceptions, our knowledge, and even our sense of self are mere illusions? And if simulations are indistinguishable from reality, does it matter whether we're living in the original universe or a simulated one? Does it change the meaning of life or our moral responsibility? This paradox forces us to confront the nature of existence itself and question whether our experiences are genuinely real or merely the product of some unseen programmer's code. Solipsism paradox. Imagine you are sitting alone in a room, contemplating your thoughts. You realize that everything you experience, the world around you, the people you interact with, the very sensations you feel, might only exist within your mind. The solipsism paradox arises from this idea. If you cannot directly access anyone else's mind, how can you be sure that anything outside of your own consciousness is real? In other words, the only thing you can be absolutely certain of is your own mind. Everything else could simply be a projection of your thoughts, a complex illusion created by your consciousness. The paradox lies in the uncertainty about other minds and the external world. Solipsism is the view that only one's own mind is sure to exist, and everything else, including other people, objects, and events, may be mere constructs of the mind. If you cannot know the experiences of others, and if the world around you could all be part of a mental construct, how can you trust any reality outside your own perception? In a sense, the solipsist argument makes it impossible to prove the existence of anything beyond your own consciousness. But here's the twist. If everything is merely a projection of your own mind, then why does the external world seem so independent, so consistent, and so capable of surprising you? The paradox is that the experience of the world, even if it is all within your mind, appears to follow its own rules and acts in ways that suggest an external reality beyond your control. The things you believe to be real behave as if they exist independently of your consciousness, which contradicts the solipsistic idea. The solipsism paradox forces us to confront the limits of self-knowledge and the difficulty of understanding what is truly real. If all that exists is your mind, then what is the nature of your perceptions and the experiences that feel so vividly separate from you? Are they truly external or just part of your own mental landscape? The paradox challenges us to question the boundaries of consciousness and to explore the fine line between subjective experience and objective reality. Gödel's incompleteness theorems. Imagine a system of mathematics, perfectly logical, fully defined, and seemingly capable of answering any question about numbers, shapes, or structures. This system is built on a set of axioms. the most basic rules that are assumed to be true without proof. For centuries, mathematicians have believed that with a sufficient set of axioms, any truth in mathematics could be derived from these axioms using logical reasoning. This belief was shattered by Gödel's incompleteness theorems, two of the most profound results in mathematical logic that fundamentally changed our understanding of mathematics. The first of Gödel's theorems states that in any consistent mathematical system that is powerful enough to describe basic arithmetic, there are statements that are true but cannot be proven within the system. These are called undecidable propositions. They are true in the system, but no sequence of logical steps can be applied to prove them. Essentially, no system can be both complete, prove every truth, and consistent, free from contradictions at the same time. This was a shocking revelation. It meant that there are inherent limits to what can be proven, even in a perfectly logical system. The second theorem deepens the paradox. It says that no such system can prove its own consistency. That is, a system cannot demonstrate that it is free from contradictions using only the tools of the system itself. To prove its own consistency, a system would need to go beyond its own axioms and methods, requiring an external framework. This is a profound limitation. Mathematics, as a formal system, is inherently incomplete, unable to fully justify itself within its own rules. Gödel's incompleteness theorems force us to confront the limitations of formal systems. They challenge the idea that mathematics, or any system of thought, can be both complete and self-sufficient. There will always be truths that elude formal proof, and even the most rigorous systems contain gaps, paradoxes that cannot be resolved within the boundaries of their own structure. These theorems remind us that certainty and completeness, no matter how logical, are ultimately unattainable in a world defined by limits. Paradox of the absolute. Imagine a concept of absolute truth, a reality that is unchanging, eternal, and independent of any observer. In this scenario, the paradox of the absolute emerges. If such an absolute truth exists, can we as finite and subjective beings ever fully comprehend it? How can something be truly absolute and universal if it is experienced differently by every observer? If all our understanding is shaped by perspective, culture, and individual perception, can we ever access something that transcends those boundaries? The paradox lies in the tension between the idea of an objective, absolute reality and the inherently subjective nature of human experience. We experience the world through our senses, which are limited and influenced by countless factors: our biology, our environment, and our personal history. Yet, the concept of the absolute suggests a truth that exists independently of these factors. How can we, being inherently subjective, truly grasp an objective and universal reality? Furthermore, if we can never fully comprehend the absolute, does that mean it cannot be known at all? This paradox forces us to ask, is an absolute truth meaningful if it cannot be understood by finite beings? The idea of the absolute seems to conflict with our need for subjective experience and interpretation. If truth is truly absolute, it should be universally accessible, yet it appears that our perceptions distort and limit our understanding of what is truly real. The paradox of the absolute challenges us to reconsider the nature of truth, knowledge, and reality itself. If an absolute truth exists, does it matter if we can't know it? And if we can never access the absolute, does that mean truth is forever beyond our reach? Or does it exist in a form that transcends our understanding, leaving us to only grasp fragments of it at a time? This paradox leaves us with more questions than answers, forcing us to confront the limitations of human cognition in the face of the infinite and the eternal. Paradox of the void. Imagine a vast, infinite void, an empty space where nothing exists. No matter, no energy, no light. Just pure, absolute nothingness. But here's the paradox. How can we even conceive of the void as a concept if it is truly nothing? To think of the void, we must use language, a framework built around things that exist. How can we describe, understand, or even imagine nothingness without invoking some form of existence to define it? The paradox of the void challenges our very understanding of emptiness. Nothingness, by definition, is the absence of all things, yet we use terms and concepts to describe it. We think of the void as a space, as something that could be empty or vacant, but these terms still rely on the idea that there is something there, something to be empty or vacant. This paradox forces us to confront the difficulty of contemplating a state in which there is no subjectivity, no objects, and no structure, where even language and thought itself have no anchor. Furthermore, in modern physics, the concept of the void is equally perplexing. According to quantum mechanics, even in a perfect vacuum, what we would traditionally think of as empty space, there is still energy. Virtual particles spontaneously appear and vanish, quantum fluctuations occur, and the vacuum is not truly empty. This challenges the very notion of nothingness, because what we think of as the void is, in fact, a highly active and dynamic state on the quantum level. The paradox of the void raises fundamental questions about existence itself. Can we truly know or understand nothingness? Or are we forever bound to conceptualize it in terms of the things we already know? If the void is the absence of everything, does it even exist in a meaningful way? Or is it a paradoxical idea that highlights the limitations of our minds, trapped in a world of existence and perception? This paradox forces us to reconsider the very foundation of reality and our ability to truly grasp the concept of nothing. Anti-time paradox. Imagine time moving backward. Instead of events unfolding in the familiar sequence of past, present, and future, everything works in reverse. Objects disassemble rather than assemble. People grow younger and actions are undone as they happen. This is the anti-time paradox, a thought experiment that flips the conventional understanding of time on its head. If we were to experience time in reverse, we would observe all the familiar processes of life and nature unraveling, as if everything were being reversed, like a film being played backward. But here's the paradox. How would we experience reality if the flow of time were reversed? In our normal experience, we perceive time as a one-way, irreversible flow. We remember the past, but we cannot change it. The future, however, is open and undetermined. If time flowed backward, how would cause and effect work? In the reverse sequence, the effects of actions would precede their causes, creating a world where decisions and actions make no sense from our current perspective. For example, instead of planting a seed and watching it grow into a tree, in anti-time, the tree would grow smaller and eventually the seed would disappear back into the ground. Events that we associate with progress, like aging or the burning of a log, would be completely reversed, leading us to experience the opposite of what we understand as life and growth. The anti-time paradox forces us to rethink our assumptions about causality and perception. If we lived in an anti-time universe, would our experience of consciousness and memory even function as we understand it today? Would we retain the ability to remember the past, or would our memories themselves also unravel? What would it mean for free will and decision-making if every action we took led to a reversion rather than progression? How could we sleep as we do if reason and decision-making led to a reversion rather than progression? This paradox challenges not just our understanding of time, but the very fabric of reality itself. It asks us to consider what it means to live in a world where the future is determined by the past, and where cause and effect are completely inverted, forcing us to confront the limits of time, perception, and our ability to make sense of the universe. Paradox of free will. Imagine you're standing at a crossroads, about to make an important decision. You believe that you are free to choose your path, that your decision is the result of your own will, influenced by your thoughts, desires, and experiences. Yet, the paradox of free will arises when you begin to consider whether you are truly free at all. If every decision you make is influenced by your biology, environment, upbringing, and even unconscious biases, then are your choices truly yours, or are they merely the inevitable result of these pre-existing conditions, leaving no room for genuine freedom? This paradox digs into the conflict between determinism and free will. Determinism is the idea that every event or state of affairs, including human actions, is the result of preceding events and causes. In this view, everything that happens, including your choices, is determined by prior causes, which may include genetic predispositions, societal influences, and the physical laws of nature. If everything is determined by these factors, then the concept of free will, the ability to make choices independent of external constraints, becomes an illusion. However, many people experience a sense of freedom in their decisions. We feel as though we are making choices, and we often act as though we have the power to choose differently. This feeling of freedom is central to human experience, yet it seems at odds with the idea that everything is determined. The paradox of free will raises profound questions about moral responsibility. If our choices are determined by factors beyond our control, can we truly be held accountable for our actions? Are we responsible for the things we do, or are we simply acting out the inevitable consequences of a complex web of prior causes? This paradox forces us to confront the very nature of freedom, choice, and responsibility. It challenges our understanding of the self and asks whether true freedom exists, or if we are merely participants in a deterministic universe, unable to escape the chains of cause and effect. Ultimately, it asks whether we can reconcile our experience of free will with the constraints of the world around us. Final paradox. Imagine that you, sitting here reading these words, are suddenly struck by a profound question. Am I real? You feel real, you think real thoughts, you experience emotions, and you interact with the world. But what if your existence is just a thought, a fleeting moment in the mind of another being, or even a projection from a distant, unknowable source? This is the final paradox. You, watching this, reading this, are left questioning your own reality. Are you truly existing, or is your entire consciousness just an illusion? On one level, the very act of contemplating your existence suggests that you are real. If you're thinking, you must exist. This is René Descartes' famous principle, cogito ergo sum, I think, therefore I am. But then the paradox deepens. If you can question your own existence, does that mean it could be uncertain? Could your thoughts, feelings, and experiences just be the result of a simulation, a dream, or a construct within someone else's mind? Could this very moment, your experience of reading this, be fabricated, and you merely a character in someone else's reality, unaware of your own falsehood? This paradox is rooted in the mind-body problem and the challenge of distinguishing between subjective experience and objective reality. In philosophy, it's often tied to solipsism, the idea that only your own mind is sure to exist. Everything around you could be a projection of your consciousness, or perhaps a series of meaningless patterns that your mind interprets as reality. So, while you may feel completely present, grounded in your body, and connected to the world, the paradox challenges the very foundation of those experiences. What if nothing you know to be true, including your own existence, is real? The final paradox forces you to question the nature of reality itself. If you are aware of your existence, yet that very awareness could be an illusion, how do you define real? This paradox asks whether there's a way to ever truly prove that you, in your entirety, are genuinely existing in the way you perceive. And in doing so, it pushes you to ponder whether any of us can ever be certain of what we really are. Perhaps all we know is that we experience, and in that experience, we find meaning. Even if we can never fully prove that our existence is real,